included 3 parts. Describing fisheries that might be taking marine mammals, characterizing the marine mammals that might be in the area those fisheries are operating in, and then prioritizing which data you might need to collect. So first, in terms of the fisheries, one of the most important things is determining which gear types might be operating. The gear type in particular is what really affects the risk to a marine mammal stock. You'll see this box on the left. We have put together just essentially like a general guide to the risk that certain gear types pose to marine mammals based on the way they operate. And like I said, this is just a general guide. There are obviously specific situations that, you know, have a little bit more context to them that we might not characterize as such. But first, you know, high risk fisheries include things like gill nets, trawls, purse seines, gears that have the capability of capturing marine mammals and forcing submergence and drowning, that sort of thing. Medium risk gears are things like trap pot, long lines, bike nets, and as I mentioned, there are caveats to these general characterizations. So one example of that might be large whales getting entangled in trap pot gear. You know, depending on the populations, that could actually represent quite a risky gear, and you know, of course, is context specific. So other things you might want to know about the fisheries that have the potential to take marine mammals are, you know, what are they fishing for, those target species, what are the characteristics of the fishery, how much effort is there, where and when does the fishery operate. So in addition to that, you want to know which marine mammals are actually captured as bycatch in a given fishery. And so obviously the best way to get that information is through direct observations like an observer program in a fishery. But we're assuming that, you know, a lot of countries, for a lot of fisheries, there aren't going to be formal observer programs. And so we were trying to think about, you know, there's lots of other ways to get information, at least a preliminary determination of what marine mammal species might be captured in a given fishery. And so that's where the indirect information comes in. And there's been a lot of work done on this in terms of talking to fishermen, conducting interviews, that sort of thing. And if you're just trying to get like a preliminary indication of which species might be taken, you know, fishermen might be willing to talk to you and let you know that they have seen or themselves captured a marine mammal in a particular fishery. You can look to stranding information. You know, if there's, you know, say some dolphins on the beach every year when a certain fishery starts up in a given season, then that could indicate that there might be bycatch of that species in a fishery. Are the fisheries in a given area using any of those high risk gears that I mentioned on the previous slide? And then also you can look at anecdotal information. There's a surprising amount of things in the popular media, social media, that end up alerting us to the fact that there might be bycatch in a given fishery. And then finally, there's opportunities to conduct rapid assessments if there's no other information available. And there's lots of work that's been done on this, one in particular for small artisanal fisheries, things like the bycatch risk assessment by Ellen Hines and colleagues, and some other co-occurrence type of analyses. And then also related to this is, you know, characterizing the marine mammal community that might occur in a given area where those fisheries are operating. So you want to know which species, which populations, is there any population structure that you need to be aware of? What's the distribution and abundance of those populations? And then of course you want to think about, you know, whether there's any conservation concerns with those populations. And some good resources to look at are like the IUCN Red List, whether a country has national designations for status of stocks, that kind of thing. And so even if there are no formal surveys, you know, you can describe where a species occurs in terms of just those sort of basic ocean zones, like whether it's coastal or on the shelf of a slope or out in the pelagic zone. And then it's also important to start thinking about here, whether you know anything about the specific bycatch levels for each species, and whether that plays into this next step, which is prioritizing data collection. So the first part of this, we were really assessing, okay, which fisheries are in a given area, which marine mammals are in a given area, to give you a preliminary sense of what data do we have, what data do we need, and then you start to think about those data gaps and say, well, obviously we are not going to have the resources to fill all of those data gaps at once, so we're going to need to prioritize. So when you're thinking about those abundance of bycatch data that might be lacking, you can prioritize according to various considerations. Some of those considerations include things like hotspots where you might have a high concentration of marine mammals and a high concentration of risky gear types. That kind of co-occurrence work that I talked about that is part of the BIRA model effort. And you can also think about the status of populations that might occur. So are they small populations? Are they declining? Are there other conservation considerations there that you might want to think about and prioritize those fisheries or marine mammals for data collection? And then, of course, one of the other things is the US's MMBIET import rule. So we didn't really give any sort of introduction on that, but I think most folks who are here probably understand a little bit about that rule. This is part of our Marine Mammal Protection Act in the US that essentially requires us to evaluate countries that want to export fish, seafood and seafood products into the US, and make sure that those products are coming from fisheries that have standards that are very similar to the US in terms of marine mammal bycatch reduction and regulatory considerations. And so as part of that process, we've defined those fisheries that we consider export fisheries and those that might be exempt from this requirement. And so if you're prioritizing your data collection and there are fisheries that have to undertake this comparability finding process for the import rule, you might want to prioritize those fisheries for data collection as well. Excuse me. Okay, so moving on to step 2. This is where you're actually going to collect the appropriate data you need to be able to quantify that abundance and bycatch. And you'll be hearing a lot more about this from both Phil and Jeff a little bit later, but I'll just give you a very, very brief overview here. So in terms of quantifying abundance, the fundamental requirement here is to assess the status of a population by looking at the availability of a nearly unbiased estimate of absolute abundance. And so there are various methods for assessing abundance. For cetaceans, we're mostly using line transect methods or mark, recapture, photo ID methods. And you'll see there the kind of percentage of those survey methodologies we use in the US. And then platforms for undertaking these surveys vary by the geographic region. So mostly out in the pelagic zone, you're using ships, on the slope and the shelf, ships or airplanes, and then in coastal or nearshore regions, ships or small boats or airplanes. And then with respect to pinnipeds, this is often based on a count of individuals when they're hauled out on land or on ice. And depending on the species, those counts can be conducted from any number of platforms like on land, boats, drones, airplanes. The surveys are usually timed to occur when the most individuals are hauled out. You can use counts of pups on a rookery, and then use models to extrapolate to total abundance. I'm sure you'll be hearing lots more about this from Phil. And then for some populations, line or strip transect methods can also be used. And again, you can kind of see the breakdown of how we use those methodologies in the US. And then with respect to quantifying bycatch, the other part of step 2, the standard approach here is a two-part process, and that requires collecting marine mammal bycatch data and collecting effort data. So with respect to the marine mammal bycatch data, the typical way to collect these data is through a fisheries observer program. And this is placing humans on or near fishing boats to document bycatch, and that can allow for estimating a bycatch rate. These programs are fairly expensive and resource intensive to undertake, so they are limited in scope. You know, obviously not every fishery has a traditional onboard observer program. And then, of course, not all vessels can accommodate an extra person, depending on the type of fishery, the deck space, the bunk space, all that kind of thing. And so an alternative that's been increasingly used are onboard camera systems or electronic monitoring. And there is kind of this assumption that those cameras are less expensive than placing humans on boats, but there's a lot of other considerations with respect to electronic monitoring in terms of like the data management and storage and review of all of the video to find those marine mammal bycatch occurrences, et cetera. And so that's just kind of the typical way. And then, of course, we need effort data from the entire fishery at the level of like how many sets are there, how many hauls. There's a number of ways to do this. You can also look at the total weight of fish landed, et cetera. They all have pros and cons, and I'm not sure if Jeff's going to get into that, but the paper certainly gets into some of that. And so once you have those two pieces from that previous slide, you can actually multiply that out by the total fishing effort to estimate the total marine mammal bycatch. And depending on the size of the fishery, that will sort of help you determine what proportion of that fishery needs to be monitored and how that varies. And so larger fisheries can have a lower percentage of effort observed. And then I mentioned a little bit about not being able to place observers on vessels for various reasons, but there's also the issue of not all fishery gear types lend themselves to a traditional observer program. So for instance, large whales can pick up gear and swim off with it. And the chances that an observer will actually document that are pretty slim. I don't think actually we've ever documented that in the US. And so mostly we end up observing the whales later and detect the fishing gear on them at that point. But so, there's a lot of techniques that people are really trying hard to develop now that help us get at that question of, well, if you can't directly observe the bycatch event, how can you estimate the impacts it's having on a population? And that so-called cryptic mortality is a lot more challenging than the typical program where you can just observe the fishery. So step 3, our next step is actually conducting the assessment of bycatch. Andre's going to talk a lot more about this later. But essentially the primary purpose of this step is to calculate limit reference points so that we can set management targets that achieve whatever particular conservation goals you might have. So reference points in general are used for managing commercial fisheries. We can use simulations to establish specific quantitative criteria, and through management strategy evaluation, also known as performance testing, we can evaluate those. In the US, we use potential biological removal or PBR as a reference point that was designed to meet the management goals of that statute. The PBR testing was done essentially that assumes a 95% probability that a population will remain at or recover to its optimum sustainable population level. And these are all concepts in the US MMBIET. So in terms of step 4, this is where we're going to use the results of that assessment to guide marine mammal bycatch reduction. And we're going to think about, which fisheries do we undertake that that mitigation effort in first, and then how exactly do we mitigate. And in terms of prioritizing fisheries, one of the exercises you're going to do this afternoon is looking at this bycatch impacts exploration tool that MMBIET, I think we call it. And so in terms of identifying priorities for bycatch reduction, you know, there's obviously lots of different ways to prioritize which fisheries you should undertake mitigation in first, or, you know, initially. And one of the simplest ways is, especially if you have bycatch estimates, is looking at ranking those fisheries by the percentage of bycatch of that limit reference point. So, you know, say a fishery is taking 75% of a stock's PBR. That might be a high priority, especially if the fishery was taking more than the limit reference point. That would be a very high priority. If you've got populations that are particularly small, those that are declining the most rapidly, those are all kinds of things you'd want to think about when you're prioritizing where to undertake those bycatch mitigation efforts. In the US, we undertake a fairly rigorous process for establishing our priorities, for establishing take reduction teams. These are stakeholder-based teams that work to develop recommendations for reducing bycatch in commercial fisheries. And our process largely relies on those three first bullets. And we sort of take them in order. Our initial ranking is based on that percentage, but then things can move up or down based on whether the population size is small or declining. And then we also bring in lots of other qualitative data in terms of like fishery management considerations and any other information that might have bearing on whether we need to, you know, convene a TRT sooner rather than later. And then in the absence of the data to do that kind of ranking, you might use some of these tools to explore the risk using population projections, for example, the MMBIET, or looking at some of those co-occurrence models, those like GIS-based mapping tools that really assess co-occurrence, like the bycatch risk assessment by RA, that sort of thing. And so in terms of actually mitigating, which ultimately is the goal of the whole process, you know, it's important to really set a goal. Where are you going to get to? How much mitigation is necessary? One of the obvious ones is, you know, yeah, you want to get bycatch below the reference point. And that's obviously important for the stock to, you know, continue growing or to recover, that sort of thing. But if you reduce bycatch to just below the reference point, then, you know, based on variability and uncertainties and things like that, you might actually be over, you might be under, you never know. And so in the US, we have an initial goal, which is to get right below that bycatch reference point, but then ultimately to reduce bycatch even further to about 10% of the reference point. So there's both a long-term and a short-term component, assuming that you get better with your bycatch reduction over time. And so I mentioned the take reduction teams. For each of those take reduction teams in the US, we have take reduction plans. And these are regulations that are intended to reduce mortality and serious injury of marine mammals in the US commercial fisheries. And so right now we've got 6 plans that cover 32 marine mammal stocks and 22 commercial fisheries. They include various mitigation measures that have had varying levels of success. I think we've only had 6 teams, 6 plans, because we're still working on them, and we don't have the resources to address additional fisheries and stocks that may have bycatch issues. And some of the mitigation strategies that we've implemented to date are things like time area closures, acoustic alarms or pingers, various gear modifications. One that is currently under development, not just in the US, but in Canada and lots of other places around the world, things like on-demand or ropeless gears, which essentially remove the vertical buoy line from the water column, so that reduces entanglement risk. Things like weak rope, which could potentially allow a whale to break free of the gear, changing hook types, things like leak hooks. Hook types, especially one thing that we've considered is how large the hook is and whether it has the capability to actually hook in a cetacean's jaw. Things like limits on the length of gear. So that could include like the length of a main line for a pelagic long line, or the length of a gill net string. Things like excluders, marine mammal excluders have been tried. Things like depth restrictions to allow animals to pass over the top of gill nets, for example. Another mitigation strategy is switching gear. If there's one gear type that's particularly risky, maybe you could switch to a lower risk gear type. Of course, lots of caveats with all of these. And then two other mitigation strategies that sort of work in concert with the above ones are things like workshops to train fishermen in how to use new gear or how to modify their gear. Workshops also include things like handling and release guidelines. We stress in the US about getting as much gear off the animal as possible to reduce further entanglement risk later on, to reduce drag, those sorts of things. And I mentioned that these have been, some have been successful, some have not been so successful. And we don't do a really good job, I think, of getting the word out on those mitigation strategies that aren't particularly successful. But there have been a number of review papers conducted and have a lot of really good information on mitigation strategies out there. The FAO has one, a very recent one. And there, like I said, there's a number of other review papers that are referenced in the paper on best practices for assessing and managing marine mammal bycatch that are really great resources. I would say that, there's been a lot of work done on mitigation strategies around the world. And if you are undertaking this process and ultimately getting to that step of mitigation, it definitely is something to spend a lot of time considering which mitigation strategies you might explore in a given fishery, because there are lots of considerations. Some of these mitigation strategies are costly, especially when it comes to buying new gears, like buying new kinds of line, for instance, or buying pingers. They are incredibly expensive. And that just might not be economically feasible in some fisheries. And then also, there's lots of other considerations in terms of implementation. How safe is it to use some of these new modifications? There's definitely a learning curve with some things like the on-demand or ropeless gear. We've really been focusing heavily on that the last few years because of North Atlantic right whales getting entangled in our lobster and Jonah crab fisheries off the Northeast US. And it's been a really steep learning curve for the fishermen. We have an awesome gear library where fishermen can check out the various ropeless systems and try them and, fill out kind of a questionnaire on how they worked and any challenges they might have come up against. And there's been a lot of back and forth between the developers on these systems to make them easier for fishermen to use and more feasible, to work into their fishing operations. And so, there's a lot of considerations when you're thinking about which mitigation strategies might be appropriate for a given fishery. And then here we are again, just back to the whole process, kind of laying everything out. And I think I will pause there and just ask if there's any questions.
There are some chats online, I think. Are you monitoring those?
I'm monitoring that. Yeah, no, okay. Nina Young dropped a link in the chat.
Great. Thanks, Nina.
But yeah, we can take, so this is the FAO guidelines that you referenced. Any questions for Kristy from people online? Oh, sorry. Go ahead.
Yeah, I just had a question. Because with getting fishermen to do something, the economic aspect is just really important. Did you do any socioeconomic analyses in this as well with your production teams, for instance?
Oh, within the take reduction teams, so economics is not an outright consideration in terms of developing recommendations for mitigation strategies, but when we undertake our rulemaking process to implement the recommendations we get from the take reduction teams, we do an economic analysis then, because that's a required part of our regulatory process. But generally, the kinds of recommendations we get from these teams, if they are just a non-starter with respect to economics, that's probably not going to become a recommendation from a team. So it's sort of informally considered in the process there. Thank you.
Other questions for Kristy?
Quick question. So, are there pre-existing, you said like, are there GIS tools that are?
Yes, there's one in particular. The question was whether there are any GIS tools available right now to look at like risk and co-occurrence, things like that. And the one that I mentioned is called ByRA, BY capital RA. And there is a really nice paper on that by Hines et al. And the citation to that is in the paper. Go ahead.
Yeah, so you outlined the US approach, and I mean, most people would say that if you go around the world, the US approach is based on far too much investment by the government. You've got more people working in marine mammals in the United States than the rest of the world put together. People in many countries don't care about marine mammals. Why should we conserve them? How does our process compare with the rest of the world, and how does NIMS feel that the rest of the world should follow the US process? I mean, I'm thinking, third world countries that can't afford to do a survey for its fish stocks, let alone marine mammals.
Sure. Well, one thing I did not focus on in the presentation here was that we do have an alternative to undertaking this whole assessment process, and that's not doing an assessment, and that's going straight to mitigation. Especially if you are looking to address marine mammal bycatch issues, if the fishery operates, seasonally, and that overlaps the marine mammal, could the fishery operate in a different season, for instance, to eliminate that overlap with the marine mammals? Or, if the marine mammals are only coming through at a certain time. Or if there's just known mitigation measures that have been tried in other parts of the world, and a country wants to just invest in those mitigation measures without conducting the assessment, that's a possibility as well. I certainly can't speak for the whole agency of NIMS and say what NIMS thinks about other countries' assessment programs or whether they should undertake assessment programs. But, I take your point that we have a lot of resources invested in assessing marine mammals in the US, and that's because we have national legislation in the Marine Mammal Protection Act that gives us those marching orders, and Congress has decided to fund lots of the programs that are contained within the MMPA. I think, there are lots of opportunities for partnerships and collaborations and a lot of expertise at NIPS where we are willing to help other countries that might be interested in doing this. And, I think the first step is what Jeff's going to do today. He's also a NIPS employee. And so I think, oh yeah, sorry, I didn't really introduce myself. Kristy Long. I work in the Office of Protected Resources for the National Marine Fisheries Service in the US. And I think, we have a lot of resources. We're happy to provide that kind of capacity building to the extent that we can. But I don't think I can say we expect everyone else to undertake our same level of commitment to marine mammal protection. Thanks for that very hard question, André.
It's friendly also.
I just have a comment on your question. I come from the UAE, and we used to have a huge issue with bycatch. And we do have a.
Can you just speak up a bit? Your microphone is there. Thanks.
Should I go there? Or
If you just project from there, it should pick it up.
Or sit closer.
so in the UAE, we did have an issue with bycatch. We had a huge issue with bycatch. Our main marine mammal that was the highest rate of mortality was the dugongs. And we took very strong measures, and we just stopped that fisheries altogether. So now in the UAE, commercial fishermen are not allowed to use any kind of nets whatsoever to reduce that bycatch problem. We have kingfish fishing seasons, and that's where it's overlapped with the dugong season. And then there's two methods of fishing kingfish. There's the drift nets, and then I don't know what to call it, the one they go around the fish.
Person.
Yeah. Because I'm not the fisheries person, I'm marine mammals. And what the fishermen do, they would do the drift nets. They would go out saying that they're doing that, and they would just do drift nets. And then the leadership there said, if they're not going to be clear with us, that's cost, there's no fishing for them. And that's what happened. But we're still getting bycatch from illegal fishing that is difficult to quantify. And that is, to us, that's the huge question, is how do we quantify the bycatch from the illegal fishing?
Yeah, there has actually been a big effort to use satellite data to look at fishing effort around the world. And it's not something I know very much about at all, but there are some methods now that are becoming available to kind of look at that.
Just to add one point, all our fishing, all our commercial fishing is artisanal fishing. We don't have huge tugboats, we don't have trawlers, we don't have any of that. So even the illegal fishing is artisanal, and it's a small scale, but the damage is huge. It's difficult to get in that. I know there's this website that talks about that. I know that. I just don't remember the name. I was hoping it would help me. It's too small of an operation to be detected.
Oh, okay. Go ahead.
Thanks. I think that is my question. As I understand it, this framework is for commercial fisheries only, or does it work also with fisheries at a substantial level for small vessels? And how do we adapt this to that scenario?
Yeah, the framework was intended to cover all types of fisheries, not just those that are commercial. In the US, we focus on our commercial fisheries. That's by and large, mostly what we have. We certainly have bycatch issues in our recreational fisheries. And that's where the catch is not being sold. It's just being kept by the individual. And we certainly have issues there that we're not doing a very good job addressing. But this process, this comprehensive framework was really meant to consider all types of fishing. Thanks for that question.
No questions online, so thank you, Kristy. So, okay, look, we're running ahead of schedule, so great.
More
So-
coffee.
Yeah. So next, we're going to turn it over to Phil Hammond, who's joining us from Scotland.
Hi, yes, Phil Hammond from the Sea Mammal Research Unit at the University of St Andrews in Scotland, where I'm sure the weather is not as nice as it is where you are. Can you see my presentation screen okay?
Yeah, it's perfect.
Excellent.
Can you turn the volume higher, please?
Yes, I can, thank you.
So my task today is to give a high-level introduction to estimating the abundance of marine mammal populations, which is a piece of the overall bycatch assessment strategy process, if you like, that Kristy just talked about. And I'm going to cover a fair amount of information in not much time, so apologies for the lack of detail in places, but you should be able to refer to the review paper that came out as part of this project, and that contains a lot of information on where to go for more information. I always like to ask the question first, why are we doing something? So why are we interested in studying the abundance of populations, in our case of marine mammals? And I rather like this quote from Mike Begon and colleagues in a textbook from some years ago, which basically says a large part of ecology is trying to understand what determines the abundance of species in places where they occur. And of course, in order to understand what determines the abundance of species, you've got to be able to estimate the abundance of species. And so I think ecology, studying the science of ecology is a really important reason why we need to study the abundance of populations. But for those of us that work on marine mammals, perhaps a far more pressing reason often is that we need population estimates to inform conservation. And this is true in a variety of legislations and conservation frameworks around the world. But picked out here the IUCN Red List assessments, where absolute population size and also trends in population size over time are really important indicators used in those assessments. Before I go any further, some quick definitions. I will probably interchange population size and abundance in this presentation. So just formally, population size is simply the number of animals in a population as defined. Come back to that in a second. Abundance is simply the number of individuals, and that could be in a population as defined, or it could be in an area and not relate to a population at all. And then within an area, density is simply the number of individuals divided by the size of that area. So I'm not going to spend much time on this. One could spend a long time on it. What is a population? And I've picked out a quote here from a long time ago by Cole, who described a population in a very biological way, if you like, a biological unit with its own population dynamics. And that's great, but it's almost impossible in many cases to implement. So here's another definition from Charles Krebs, which is at the other extreme, if you like. It's basically population in a place and a time, boundaries in time and space are vague, usually fixed by the investigator arbitrarily. So basically, a population is whatever you want it to be. And that can be what you end up having to do, but it's also not very informative in the context of estimating abundance. So in marine mammal world, when we estimate abundance, we often do this for assessment or management units. And I pulled out a couple of examples of this here in the bottom in the line drawing. These are the North Pacific minke whale subareas that are used by the IWC Scientific Committee in simulations of its revised management procedure. So estimates of abundance are required for each of those. And on the right, similarly, these are assessment units for harbour porpoise in the European Atlantic as used by the International Council for the Exploration of the Sea. So moving on, it will be very nice, of course, if we could simply count the number of animals in a population, but this is in almost all cases impossible. And you can see why, because issues of access, marine mammals are obviously marine or live in the, lakes and rivers. Some can be highly mobile. Most of them spend all their time underwater. And quite a lot of marine mammal populations are very large and live in large areas. It's simply impossible to count them. And we should also not forget that actually small populations, so ones with very few animals, are also very difficult to count. And I've simply illustrated this here by showing some pictures of the vaquita and a picture on the right from a paper by Barb Taylor and co, not counting vaquita, which is effectively impossible, you hardly ever see them, but in how you estimate the abundance of vaquita in the tiny area that they live in the northern Gulf of California. So we can't really count in almost all cases, we have to estimate. An estimation in its simplest form simply means collecting a sample of data of some kind and then extrapolating from that sample to the whole population or the area that you're interested in. And to extrapolate from a sample to something else involves using a statistical model of some kind. And statistical models make assumptions. And you'll hear me say this probably several times in this presentation, assumptions are really important because if you get them wrong, then your estimate of population size or abundance can be biased and you will not know it. And then you'll be providing bad information to conservation managers, which is not a good thing. Assumptions are typically about the data, about the sample that you're collecting of data being representative of the population so that you can extrapolate it without bias to the population. but you also make the assumption that the model you're using to extrapolate is appropriate. A brief word about accuracy and precision. In the world of estimating abundance, these mean two completely different things. Accuracy is whether or not your estimated value is close to the truth, whether or not it's biased. And you typically will not know whether your estimate is biased. All you can do is make sure, or try and make sure, that the assumptions of the method you're using are not violated and are met, because if they are violated, that can cause bias and you'll get the wrong answer. So accuracy is all about bias, and assumptions are important to make sure that you don't get a bias. Precision is the measure of confidence in our estimate, whether or not it's biased. And we typically measure this by things like standard error, CVs, or a confidence interval. And CVs and confidence intervals, measures of precision, are dependent on sample size. The more data you have, the more precise your estimate will be. But they also depend on some things that you can't really control. Natural variation in group size in species, for example. Nothing you can do about that. You just have to live with that. And also, they rely on the fit of our statistical model to the data. So if the model doesn't fit very well, you'll get a larger confidence interval around your estimate. So this is just a flag that's difference between accuracy and precision, because I think that's sometimes not fully appreciated, that these are two different things, but they're both important. Typically in any study, we would aim to minimize bias, so maximize accuracy, but also maximize precision, so have the smallest confidence interval around our estimate. And given limited resources that we always have when estimating abundance, this is typically a compromise. So we are not necessarily going to get a completely unbiased estimate, and we're not necessarily going to get one that's as precise as we want. But really, the task of estimating abundance and population size is really to try and achieve this minimized bias and maximize precision. So to illustrate this, this schematic, suppose we have a number of replicates of estimates of abundance. These are the rug plot shown on the right. The true abundance is shown by the blue arrow, and our estimate is essentially the average of those replicates is shown by the black arrow. So in this case, our estimate is very close to the truth, and also most of those replicates are fairly close together. So we would say that's a precise estimate, because if you calculate a confidence interval, it will be pretty tight. Here's an example where we also would have an accurate estimate because our estimate is close to the truth. But now there's a much bigger range in our replicates. So if we calculated the confidence interval there, it would be much wider. So that would be an imprecise estimate, but an accurate one. And then the other two combinations are where we might have a precise estimate, but actually in this case, the third one down, it's inaccurate because our estimate is a long way from the truth. And then the bottom one looks like the worst of all worlds. It's an imprecise estimate, but it's also inaccurate. So these are the four situations you might get. And remember that accuracy and precision are usually not related. So I would ask the question, I'll ask it rhetorically so as not to spend time waiting for people to answer. Which of these four situations is worse? And you might think, well, the last one's worse, obviously, because it's inaccurate and imprecise. But my personal view is that the third one down is the worst, because if we're providing information on abundance and population size to conservation managers, we do not really want to give them a precise estimate that looks like we've got lots of confidence in it, but actually it's miles away from the truth. And because we violated our assumptions of the methods. So this is why I keep going on about assumptions being so important, because I think that third one down is not a good place to be. And the way we can avoid that is by meeting our assumptions and not violating them. Tessa mentioned in her introduction about these flowcharts that we've got in the papers that we published that arose out of this project. And this is the one in the abundance paper. And obviously no time to go into this in detail, but essentially it asks the question, what is your species you're interested in? What kind of data are you collecting to try and estimate abundance? Those are the ovals. And then the diamonds and rhombuses are about analysis and additional data that you would use in order to estimate population size. And what I want to do is use this to show you three ways of estimating population size abundance of three fairly typical situations in the marine mammal world. The first one is, suppose we have a pinniped, a seal or a sea lion, and we have haul out counts. These are all age population, all age haul out counts, the whole population. So we can count them on the haul out sites, and then we need information in the diamond on the proportion of the population or the percentage of the population hauled out. And we can then extrapolate our counts using that proportion to get an estimate of population size. If one counted pup counts, the orange squares here, then one would need either some kind of multiplier or a life table or a population model to extrapolate those pup counts in order to get your population estimate. So this is the first example I want to show. Count a definable part of the population, pups or all age haul out counts, and then extrapolate to the whole population. And just to illustrate these at a high level, two examples from the UK. One is how we estimate abundance of grey seals around Britain in the UK. We count the number of pups born using aerial surveys, and we do that multiple times during a pupping season. We then use those counts from the aerial surveys to estimate total pup production, and that's got a model in it in itself. And then we take the total pup count and we fit a population model to those pup counts in order to estimate the total population size. And for that, we need information on fecundity and survival, age structure. So if you're going to do this using a population model, you'll need to find information on those elements, as well as just doing the count. And the papers here will describe that in much more detail. The example I want to give you is about counting pups, not counting pups, counting all the animals in a population, and they may be hauled out on land or on ice. And then to extrapolate, you need to estimate the proportion of the population that's hauled out. This picture shows a thermal image of harbour seals, which are the white blobs hauled out on the grey land, and the black is the sea. So counting harbour seals when they're hauled out is very easy to do using this method. And if you use ordinary photography, that's a problem because the seals really don't show up against the rocky background. So the study I'm going to use to illustrate this is quite an old one from 1997, but it's a very good illustration of the way the method works in practice. The paper is about estimating the abundance or population size of harbour seals in an area called the Moray Firth in northeast Scotland. And the map in the middle shows the study site, and the black dots are where the seals hauled out, and these are tidal haul out sites. So the first part of the method is to count your seals. You can do that from a boat. You can do it from a vantage point on land. You can do it perhaps better from the air to get a picture that looks like the one on the right, where it's fairly easy to count the seals. However, in our studies, we have to be a little bit careful because in this picture, these are harbour seals and these are grey seals. So you can easily see the difference here just from the way they haul out. They're spatial aggregation of the grey seals and harbour seals spreading themselves out more. But just as a flag that it's important to make sure you're counting the right species when you do this, if there are mixed species haul outs. And then the proportion of the population hauled out is estimated from telemetry. And this is an old study, so we were using simple VHF telemetry, as shown in this picture. Nowadays, we would use satellite linked or GSM tags for this. Some things to consider when implementing a method like this. First of all, when do you do your count? And this picture here shows the mean haul out count of harbour seals in this area month by month over a whole season. And you can see that there's quite a strong seasonal pattern, with most of the highest counts being in the summer in June, July, August. Excuse me. So in this study, we did the counts, took the counts from June and July as our counting period, but we didn't use them in August because in August, harbour seals molt and the tags fall off, and then we don't have any telemetry data to extrapolate the count from. So just in June and July. Here's a picture of the proportion of low tides that the tag seals hauled out on. And you can see there's no pattern diagonally, time of day. It's pretty much flat. So you can count whenever you like, or obviously during the day. However, because it's a tidal area, tidal system, there is a strong tidal pattern in when the seals haul out. And you can see here, this graph shows the number of hours minus or plus low tide. And you can see that within about 2 hours of either side of low tide, the counts are pretty consistent. So that's when we did our counts in terms of the tidal cycle. And for the telemetry, we used VHF telemetry, and we actually estimated the proportion of low tides when the counts were made that each individual spent ashore, and then took all the data that we got to estimate the proportion for the population. And we tagged the seals obviously before the counting period in the spring so that we got data during the count. And note here that we got data for 6 years here and combined them, and I'll come back to that in a moment. And then the statistical model we're using for extrapolation here is simply, we're taking the average count in the area and dividing by the proportion of low tides that the individuals spent ashore. So that is our model, and it makes various assumptions, which I'll come back to a couple in a moment, but it's a pretty simple statistical model to estimate abundance. I don't want to dwell on the results here because that's not the point, but just for the record, about 1,000 seals counted. Proportion of tides hauled out was between 50 and 70% for males and females, giving a total population estimate that you see there. And it's pretty precise. The CV is only about 0.06, which is a very low CV for estimating abundance of any form. Points to consider, though, which are important. Timing of the count we talked about. You really want to try, I think, and maximize the number you're counting, because then that has the smallest error around it, and that will maximize the precision of your overall abundance estimate. And that's important because maximizing the count is important because the correction factor using telemetry typically is much more variable. So you'll increase your variance if you have to correct more. So I would always argue for getting as high a count as you possibly can, which is why the timing of the count was important in this study. One thing that's an assumption here is there are various haul-out sites, as you saw on the map before. So what if animals move from one haul-out site to another in between the counts? So we were double counting or missing animals. Well, that would be a problem if we were. But actually, you can see from the telemetry data that that wasn't happening during our count. So we were fairly confident we were meeting that assumption here. But the one I want to come back to is that the telemetry data were averaged over 6 years, and we're estimating abundance here for just one of those years. What if the haul-out behavior was changing interannually, or maybe there was less food in the early period and more food in the later period, seals spending more time or less time ashore? We assume that is representative of our population estimate in 1993, but actually it might not have been, and we really don't know whether that assumption was met or not. So there is a potential for bias in our estimate here. Okay, moving on to method number 2, back to our flowchart, and this is now for a cetacean, where we're using photo ID individual recognition data, the blue boxes, and we're using mark recapture analysis to analyze those data in order to get our population abundance estimate. You'll see at the bottom there's a footnote which says correct for population identifiable in the population as appropriate, and we do that in the study I'm about to describe, so that's important then. Before I get to the example study, some real basic mark recapture for you. The idea of the basis of all mark recapture really can simply be described as going out and capturing a sample of animals, and we'll call that N1. Then you go away and do something else, come back later and capture a second sample of animals, we'll call that N2. And then in that second sample, you see how many were already marked from the first sample. These are the recaptures, and we call that M2. And then, if the various assumptions of this are met, the proportion of marked animals in the second sample, so that's M2 over N2, should equal the proportion marked in the whole population, which is the number you counted in the first place, divided by population size, which is unknown. And then if you turn that equation around, you get the Peterson, so-called Peterson or Lincoln index estimator, which is simply the product of the two sample sizes divided by the recaptures. If you were really doing a two sample estimate like this, you will probably use the Chapman modified Peterson estimator, which is this, because that minimizes small sample bias and allows you a simple way to estimate the variance and therefore standard error and confidence limits. But of course, most of our studies are using multiple samples, not just two. And these allow for more complex estimation methods, including closed and open models. And no time to go into those details now, but you can look in the paper for more descriptions of that. But most of our studies will not be based on this simple two sample estimator. A word about the assumptions. Some of them are about the data themselves. So we assume in any mark recapture study that marks are unique, no two animals are the same, marks cannot change or be lost, and also that you recognize and correctly record any marks on recapture, which may seem like an obvious thing, but actually it's surprisingly easy to get that wrong. And if you do, and you have a small sample size, that can make quite a big difference. Excuse me. All these images on the right are of, well, there's a tagged sea otter there, but also photo ID of humpback whales, this female grey seal. These are all good marks that can be used for mark recapture. Assumptions about basic models. So these are the conventional simple models. One of the main ones is that all animals within a sampling occasion have the same probability of being captured. And there's two parts to this. One is that when you mark an animal, it doesn't affect the future catchability of that animal being seen or being caught. And the second one, and much more important really in most studies, is that individuals do not vary in their capture probabilities within a sampling occasion. And this is commonly known as heterogeneity of capture probabilities. This, in my experience, almost always occurs in any mark recapture sample. And so it's important to consider that. Come back to that in a second. If you're using closed population models, closed here means demographically closed. So you're assuming there's no birth, death, or permanent immigration or emigration going on during the period of the study. If you have a long-term data set, clearly that's not going to be the case and you'll want to use open population models. But open population models don't estimate abundance very well. And typically they can't take account of heterogeneity of capture probabilities. So it's quite common to use closed population models to take advantage of being able to account for heterogeneity and finding a way to make sure the assumptions of closed populations are met within the analysis. So that can be quite an involved thing, but it's something worth bearing in mind. Example 2. This is a study we've been doing in the east coast of Scotland, which started off in the Moray Firth, the same area as the previous example for harbour seals, back in 1990. And the aim here was to estimate the population size of a small bottlenose dolphin population living in this area. Core area was in the Moray Firth, and the mark on the animals is photo identification. One of the key things to consider in any such study is how you turn your pictures into data to be analysed using mark recapture methods. And in terms of representativeness of the sample, we ask ourselves the question, were all the animals in the population available to be sampled? And typically the answer is no to this, but it's an important question to ask from the front, right up front. In our study, we had 3 years of data and we followed the solid red line in a typical photo ID survey in multiple occasions, because that's what we were able to do logistically. But in the 3rd year of the study, we're also able to do more coverage of the area by following the dashed line. So we actually sampled a larger area where the population lived. And this is a tricky thing in any of these studies, and I don't have time to go into any detail here, but the larger the area that the population lives in that you can study, the better, because the less assumptions you'll have to make. We use images of the dorsal fin of these bottlenose dolphins, and we only use the nicks and notches in the trailing edge, even though most animals have marks all over. And the reason we do that is because these other marks can fade over time, and we want our marks to be permanent. So we use good quality photos to get the best images, so we can look at the nicks and notches and identify the animals, and we call these well-marked animals. So the analysis is to estimate first, apologies for my lingering post-COVID cough, is to estimate the number of well-marked animals using mark recapture methods. And we did this for all 3 years using data from the summer, multiple sampling occasions. And importantly here, we use closed population models because we were pretty sure we'd need to account for heterogeneity of capture probabilities. So we used a model within a year and made the assumption the population was closed within a year. In those days, this is quite early on in our study, we had separate estimators for left and right sides. What we do now is combine them because you can see the nicks and notches from both sides, so we don't distinguish. Then the second part is to estimate the proportion of these well-marked animals in the population, because not all these animals are marked in that way. And the way we did that was to take all the fully photographed groups where all the individuals were photographed, and then to count how many were well marked and how many were not well marked. And then you know how many individuals were not well marked, because otherwise that's quite tricky. And then we could estimate the proportion in the population. And our population model here is our extrapolation model is kind of twofold, because we've got a mark recapture extrapolation, and we've also got the extrapolation to account for the proportion well marked in the population. But overall, it's a pretty simple way of estimating abundance. Again, results are not the main point here, but just for the record, the number of well-marked animals was really quite small, 70 or 80, depending on the side, and the proportion in the population was around about 0.6, giving a population size estimate at that time of 129. And again, you'll see the CV is 0.12, 12%. That's pretty precise for a population estimate. The points to consider, was our sample representative? Well, we don't really know, because you rarely know really what the total extent of the population is and how the animals are mixing up within the area. But the aim, I think, should be to go for wide spatial coverage if you can. Choice of mark in some ways is obvious, but an important point here is the mark must last longer than your study period. So that's why we didn't use these superficial or transitory marks like rake marks or skin lesions, because we wanted our marks to last longer than our study period, in this case 3 years. But now we've been doing this for 30 years, so long-lasting marks are really important. Even though we tried hard in the field to give every individual the same chance of being captured, we were pretty sure we had heterogeneity of capture probabilities. And indeed, the model that we ended up using to estimate did have to take account of heterogeneity. So to minimize that problem, one should photograph as many animals as possible, because that will, the more animals you've got, the less heterogeneity is a problem, and make sure you use an appropriate model. And if you want to estimate the proportion of well-marked animals, that can be quite tricky. And the best way of doing that, I think, is to try and photograph every animal that you encounter. That will give you the best data to do that. So the final method, back to our flowchart. And this time we're going to choose a cetacean that we're going to estimate the population size of using a visual survey. And the example I'm going to use uses both ship and aerial survey using line transect methods. And in this case, we did not need to account for using diving behavior data, but if you did, then you would use that. So we'd follow those blue boxes along to the population abundance estimate. And as I think Kristy said, most of these cetacean estimates in the US marine mammal assessment are estimated using line transect estimates. So that's the method. Basically, if you want to do a line transect estimate, you need to define a survey area. You have to have an area defined because you're sampling area in line transect. You're not sampling individuals. And then you design your survey transects to provide a representative sample of that area. That's the critical thing. And to do that, really, you should involve a random starting point, so that when you choose your random starting point, obviously the transects appear, but before you choose a random starting point, every point in that area has the same chance of being sampled, so you guarantee a representative sample. I'm going to illustrate this using this picture and first talk about strip sampling. So in this picture, we've got a survey area, 50 by 100 units. The size of the area, therefore, is 5,000 units, capital A. The green bars and the dotted lines in them are transects and the area searched around them. So the total transect length is 5 times 50, which is 250. And the width of half the strip here is 1 unit. So the total strip around both sides is 2 units. And that's the green area you can see in the picture. So the area actually sampled, is twice the width on one side, twice the width, multiplied by the total length of the transects, which ends up as 500 units. And so our coverage, nominal coverage, because you're dividing a linear measure by an area, is 500 over 5,000. So we're covering 10% of the study area here. Then We count the number of animals that we see in those strips, the green strips, and there are, believe me, 36 red blobs in those green strips. And that's our sample size little n. And then our estimate of density, which is what we're trying to estimate using line transect sampling, is the number we count in our sampled area divided by the sample area, which is simply 36 divided by 500, which is 0.72. So our sample density is 0.72 animals per square unit. Then to get abundance, we simply multiply by the total survey area, which was this capital A 5,000. So we do that calculation and we estimate there are 360 blobs in this picture, black ones or red ones. So that's strip sampling where you assume you see all the animals in the green strip that's been sampled. Line transect sampling or distance sampling does not make that assumption, and that's what I want to move on to now. Imagine this is your line transect and the dotted lines above and below bound the nominal area that you're searching around the transect line. That arrow there is you, the surveyor. You search along these lines, collecting data on how far you've traveled, and usually on the sighting conditions like the Beaufort scale or other things, swell height and so on. And when you see a group of animals, cetaceans, shall we say, you determine the species and the size of these groups. So those are your data. So we know, adding up all the transect lengths, capital L, we know the width of our nominal strip, and come back to that in a second, is W on either side. So our nominal area searched is 2LW, just like it was with strip sampling. But we do not assume here we can count everything in the strip we're searching. And it's simple physics. The further away you are from the transect line, from the survey vessel, the harder it is to see something. So you expect detection probability to drop off away from the transect line. So we also collect data on perpendicular distance, which might be measured directly if you're in an aerial survey from that point, or if you're on a ship, it will be estimated from the radial distance and the angle, and then using simple trigonometry. So you've got your set of perpendicular distances to all the sightings. Then the analytical part is at the end of the survey, you will end up with a histogram that looks something like this, where the histogram bars are the number of sightings of the species you're interested in seen at different perpendicular distances away from the transect line, which is 0, out to your nominal strip width, which is W. Line transect analysis or distance analysis fits a detection function to those data, which you expect to drop off the further away you are from the transect line. We make the assumption, an important one, that on the transect lines itself, the probability of detecting animals is 1. That is, you always see everything on the transect line. I'll come back to that in a minute. So if you were doing a strip transect, you would assume you saw everything all the way out to your strip width, W. So that blue hashed bar there. And what you do in line transect analysis is essentially trying to account for these missed animals because they were less detectable by estimating the average detection probability, which is simply the area under the red curve where the histogram bars are, divided by the total blue rectangle, which assumes that you see everything all the way out to the distance W. So this is your average detection probability. And sometimes in the literature, you'll see this expressed as a effective strip width or effective strip half width, ESW, which is simply the total width, maximum width divided multiplied by your detection probability. So say, for example, W here was 1,000 and your probability of detection was 0.6, then effective strip width would be 600. So that's what's going on in the estimation of the detection function in line transect analysis. And then the simple equations, pretty simple to estimate density, are take the number of groups you've seen, assuming you've got groups of animals, which typically for cetaceans we would have, and multiply by mean group size. So the top line of that equation is the number of individuals you've seen. And then the bottom line is the area that you've sampled, which is the length of the transect twice the width multiplied by the average detection probability. So that's your simple density equation. And then to get abundance, you simply multiply by the size of the area again, just like with strip transects. And that's what you need. Note, if you do not see all the animals on the transect line, which in line transects of marine mammals in the sea, you typically would not, Then ideally you would divide your estimates of density and abundance by a quantity typically known as G0. And G0 is the estimated proportion of groups that are detected on the transect line. So it's between 0 and 1. The higher it is, the closer you get to meeting that assumption that everything's seen on the transect line. But if you don't correct for that, you're going to underestimate abundance by an unknown factor. So sometimes it's possible to assume that G0 is 1 and you don't have any bias, but typically that's not the case. Briefly about assumptions before I move on to the example. The survey area being sampled representatively, we've already talked about that. We've just talked about all animals groups being detected on the transect line and what you can do if that's not true. We also assume there's no movement of animals either in randomly or in response to the survey vessel. Random movement is typically not a problem. Movement in response to the survey vessel could be a problem in some situations, and it gets a bit complicated to try and deal with that. And I don't really have time to go into that today, but there's information on that in the review paper. We also, as in all methods actually, assume we collect data accurately. Perhaps worth flagging here because collecting data at sea is not easy. Transect length is usually easy, but there's always can always be some doubt in species identification. Group size is notoriously difficult to measure. Distances and angles can also be subject to error. So the aim here is to try and collect your data as accurately as possible. And the last one is really simply to ensure you get an unbiased estimate of variance. So these are the assumptions we're making when we do a line transect survey. And the example I want to use to illustrate this is one we've been involved with over here in Europe for quite a long time now. And this is the so-called SCANS surveys, where we estimate cetacean abundance in the European Atlantic. And we started this in the 1990s. And the motivation was really to give some abundance estimates to put into context the estimates of Bycatch that are starting to be coming out, which seem really quite high. And we had no population abundance estimates to put them into context. So the idea was to estimate abundance of several species at an appropriately large spatial scale, because these are quite widespread populations, and doing little surveys in little areas will not necessarily, or almost certainly will not, give you the best picture. It started in 1994, and you can see the survey areas here in the overall study area for the surveys we've done prior to the survey I'm going to talk about in a bit more detail. 94 was mainly in the North Sea there and in the waters to the southwest of Britain and Ireland, and also into the Danish inner waters and the Baltic. Blue means the area was surveyed by ship, and pink means it's surveyed by air. 2005, we did it again, and this time covered all European Atlantic shelf waters. Again, pink is aerial, blue is ship. And then we didn't cover offshore waters in 2005. So in 2007, we did a ship survey to cover waters out to most of the 200-mile EEZ in most of European waters by ship to sort of add on to the 2005 survey. The survey I want to talk about in a little bit more detail in a few minutes, is so-called SCANS 3 survey, which happened in 2016. This was the survey area. Again, pink is aerial and blue is ship. And we had 7 aircraft, 3 ships. We did the survey as always in midsummer, July, August, and you can see the size of the survey areas. There were some other surveys going on at the same time. The Irish Observe survey had data from 2016 as well as 2015. That's the green area around Ireland. And also the Faroese North Atlantic Sighting Survey was happening in 2015, the year before. So that's the yellow area, and we designed our surveys so that the survey boundaries could be contiguous. The searching effort realized looked like this, so quite good coverage from the air in the pink, excuse me, and also in the ship surveys, fairly good coverage. There's a purple block there between Norway and Sweden, where the weather was bad on the planned ship survey, so we did it by air as well. There's quite an extensive survey with quite a lot of coverage. The methods we used for ship and air are these. So for the ship survey, we used a double team method. So we could estimate G of 0, the proportion of animals seen on the transect line, because we believe that was really important because one of our target species was harbour porpoise, which are notoriously difficult to see. So the primary platform was there in the main observation platform, and the primary team searched with binoculars in the way that you typically would for any land transit survey, relatively close to the ship. The second team was called tracker team, and they were in the upper platform, and they searched with big binoculars further ahead. And the idea there was to pick up animals and then track them back towards the vessel as the vessel approached, and to determine whether or not the primary team picked them up. And so then, excuse me, you've got these two sets of data for tracker and primary, and you can use the primary data to estimate the detection function in the way that we described earlier, in the normal way. And then the tracker primary data combined are a kind of mark recapture experiment to see what proportion of animals that you miss or see on the transit line to get your estimate of G of 0. And this is easy to implement in program distance or the R library thereof, called MRDS, mark recapture distance sampling. So that's what we did for the ships. For the air, we use Spartanavia aircraft, which are quite commonly used in Europe, with bubble windows and an declinometer to estimate or to measure perpendicular distance. And we used, I'll just illustrate this for a minute, we use this so-called circle back method that we found to be quite a good method for estimating G of 0. So the idea is you fly along your transit line going from right to left, where the arrow is. And then if you make a sighting of porpoises in this case, then you put the protocol into operation for the circle back, and you fly along for 30 seconds and then circle back in a backwards direction parallel to the line you just surveyed. And then you rejoin the transit line and survey that piece of track again. And then you carry on surveying after you might or might not see another sighting of a porpoise. You don't know if you do see something, you don't know if it's the same group. So this is a probabilistic way of collecting data to estimate G of 0 using double platform data in a sense of passing over the same line twice. And the analysis is done in a program called Racetrack, which allows you to estimate probabilistically the proportion of animals that you've seen on the transit line. So that's what we do for the aerial survey. And we do that for porpoises, dolphins, and minke worms. The results, again, is not the main point here, but just for the record, these are the distribution maps of sightings for some of the species, and also the estimates of abundance we got. These are sadly not yet published, but they are in a report which is publicly available with this URL. Lots of porpoises, top left, as you can see, over a large part of the northern part of the survey area, estimate of nearly 500,000. But the things and the other species, some of them are quite large populations of common dolphins, striped dolphins, some of them much smaller, just 10,000 or so. The points to note here, I think, are twofold. One is the CVs are actually pretty good for a large-scale land transit survey. Barb Taylor's written a paper about how difficult it is to get precise estimates of abundance, and we were quite happy that we got such good CVs, even though they may seem not that good. Actually, they are pretty good. The other thing to note is that if we had not corrected for G of 0, these estimates would all have been smaller. And for example, for harbour porpoise, G of 0 comes out around about 0.3, about a third. So if we hadn't corrected for G of 0, all our estimates of harbour porpoise would be only a third of what they came out with. So we will be severely underestimating population size. So important to make sure you do estimate G of 0 if you can for the species where you need to. So points to consider for the scan surveys. We realized we had a danger of getting biased estimates because of G0 and also potentially getting low precision. So what we did was design the survey to get relatively high survey coverage, and we did the timing in mid-July, which is when the weather's better and also when actually the main target species porpoises are spread out, not aggregated, which allows you to get a more precise estimate because you don't have clump distribution. So we did that, and to do that, we had to raise quite a lot of money. So this relates to Andre's question earlier. What about countries that don't have that kind of money? Well, yeah, it's difficult to do this kind of surveys if you don't. And the second point there is that we use the double platform shipboard and the circle back aircraft methods to estimate G of 0. And if we hadn't been able to do that, we would have got really quite strongly underestimated population size estimates for most of these species. The other thing is a logistical thing. These are large areas, and they require major surveys, major organization, lots of money, coordination in our case between lots of countries. So those, you don't do this lightly, and we've only done these every 10 years, and now we're doing them every 6 years. So this is a considerable commitment in time and money and in resources generally. So just to summarize, I've explained or described very briefly, high level, 3 different methods that are commonly used to estimate abundance for marine mammals. And I've illustrated them on this flowchart that we've got in the paper. And I would encourage you, if you're interested in this or interested in more detail, look at the review paper. It's a good place to start for getting more information and sending you to other material that's been published on how to do this in different situations for different species. And I would just finish by saying assumptions, assumptions, assumptions. Make sure your method assumptions are considered right from the start and you design your data collection accordingly. And that determines how complex your analysis needs to be. And of course, sometimes we need complex analysis, but the simpler you can make it, the better it is, and the better estimate you'll get, I think. So I will finish there. Thank you.
Thank you so much, Phil. That was fantastic. And I'm sorry to make you talk nonstop through your post-COVID recovery for like 45 minutes. I'm sorry. We do have about 5 minutes before our break for any questions for Phil. Yeah, I see in the back. You want to come close to the owl so he can hear you?
Yeah, I had a question regarding the circle back method. Did you have to account for any autocorrelation between those, given the, like if you went the first time and you saw something and you circled back, you might have a different level of searching, sort of like in occupancy when it's on connected trails, you have to account for autocorrelation. They're not actually independent samples.
Yeah, really good question. I don't know if everyone could hear that, but do you have to account for autocorrelation when you're doing the circle back? The answer is you have to be really, you have to consider that. And there's 2 things here. One is, do the observers change their searching behavior when they've just flown by a sighting of, say, a porpoise, and they're circling back and they know they might see another porpoise? And of course, that's a real issue. And our observers we think are very well trained, and they try really hard not to do that, to be looking harder when they do the second one. But the other thing is to do with dive times. And if you, for example, say porpoises dive consistently every 4 minutes, and or say every 3 minutes, and you do a circle back and you pass them by every 4 minutes, when you see them the first time, they're all going to be underwater when you go back the second time. So you have to consider the dive pattern, the dive times, when you set up the interval the interval between the first pass and the second pass. So these are really important points. And if so if anyone's going to think about doing this, I would encourage them to read the papers on how the method is implemented, because these are important issues.
So how would you do that for multiple species then that would have different dive times?
Yeah, tricky. And the data we have, most dolphin species, minke whales and harbor porpoises, although it may seem improbable, they actually have quite similar dive patterns. So we were quite confident using the same protocol for those different groups of species that we were okay. If you were doing a deep diver, forget it. It's not going to work because they can be underwater for so long. So circle back does not work for everything. And basically that's it. And it's a great method for the species what it works with, but it doesn't work for everything.
And give me a thumbs up when you see my PowerPoint. I see you, Andre, so give me a thumbs up. Yep, okay, great, awesome. Okay, so most of what I'll be talking about, we'll be working with, comes from this paper in the special research topic that I suspect most of you are familiar with. This was sort of the Bycatch estimation review article, you might say, in that issue. And this session is going to be divided into 2 parts, one before lunch, one after. And this is what we're going to cover in round 1. And I want to talk a little bit about what we'll be covering today and what we won't be covering today. So this session is really going to focus on estimation concepts, especially with respect to survey design considerations and some basic statistical considerations. So the idea is that you have used some methodology, whether it be observer programs or interview types of data or self-reporting or other, but you have some kind of data that serves as a basis for doing statistical estimation to come up with bycatch estimates. So we're not really gonna talk about the different methods for collecting those data. We're gonna talk about study design elements that would apply to any approach you might use to try to collect bycatch information. And we're also not really going to talk, we're not going to talk about the sort of pros and cons of the different data collection methods, such as observer program versus log books versus interview types. There are some very important differences with scientific fishery observer program data being strongly preferred when that is able to be obtained. And those discussions are detailed at length in the review paper, but it won't be the focus of this discussion. And we also won't be talking about how to design observer programs in the sense of implementing the complex logistics of carrying out observer studies on the ground. So we're really focusing more on concepts from the standpoint of study design, statistical estimation, and so on. The math for bycatch estimation is pretty simple. Essentially, it boils down to you needing to obtain an estimate of bycatch mortality for some defined animal population. And Phil talked a bit about defining populations. That was quite useful segue. And importantly, your bycatch mortality estimate will also be time specific. And most typically, we see things like bycatch estimates per year or per fishing season. So the bycatch estimate is a function of basically these four parameters, the bycatch mortality estimate. One, how many animals are in the system? So all else being equal, the more animals you have, the more animals will get caught. Fishing effort, same thing, more effort, more interactions. This catchability term, which essentially scales your animals and fishing effort into a number of catches, right? And so you can think of catchability as like a per capita probability of an animal getting caught by a single unit of fishing effort. It's not something that's typically estimable given marine mammal bycatch data that we have, but we'll see how in the next slide how we're going to make that term go away. And then we need a post-catch mortality rate estimate, right? So you catch a certain number of animals. They don't necessarily all die. Some are caught alive and released. That is dependent on the species and the gear characteristics. So, for example, we're more likely to catch and release a cetacean caught on a longline hook than we are a cetacean caught in a gill net. This is a difficult term to estimate as well. And the fisheries that we're often most concerned about are net fisheries with cetaceans. It's not exclusively the case. They get caught in large trawls. They get caught on longline hooks. They don't tend to fare well in trawls, and they don't tend to fare well in nets. And simplifying and conservative assumption is often that we assume this post-catch mortality rate to be 1, if it's not something that can be estimated directly. And there's a little bit more discussion about that in the paper, but that is all I'm going to be saying about that term today. We're typically going to replace the product of N and C, population size and catchability, with this term that we'll call B here, and which is bycatch per unit effort. And that is what we are most typically going to be estimating in our observer data or our interview data or our logbook data or whatever it is we're collecting. The rest of this exercise today is going to be going through examples of estimating this BPUE term under an assumption that the fishing effort is known. In practice, fishing effort is not always known, so it depends how much we know about our fishery, and the effort itself might also need to be estimated. And pretty much all of the concepts and considerations that I'll be mentioning in the context of doing a little practice observing bycatch, estimating bycatch effort will apply to estimating fishing effort as well, such as making sure we're obtaining representative samples of let's say fishing ports or interviews with fishermen to describe the fishery. We might need to do some statistical sampling to quantify effort itself. But we're going to assume for right now that we know what the effort in the fishery is, that we have a good vessel registry system, or we have, so number of boats are quantified and fishers are reporting logbook data that's describing how many trips and sets they took and where those occurred and so on. So it is important to have that information. And if it's not available by the fishery management organization, then that's something that the researcher needs to estimate as well. But we're going to focus more now on estimating this BPU or BPUE term. Okay, so again, BPUE best estimated from Scientific Observer Program, but there are other ways to go about it sometimes. Fishing effort, I kind of mentioned that already. So here's a really important tip, really important point to make, is that when you're going about doing your estimation, the fishing effort and the BPU units have to agree, right? So if you are doing some kind of scientific observer study, you're putting technicians on boats, and they're quantifying the number of bycatch events that were observed for so many sets in the fishery, like so many net sets or so many long line deployments, then your fishing effort for the fishery has to be quantified in those terms as well. So if and here's like just a little thought experiment. So if you've quantified BPUE and animals caught per gillnet set, and your fishing effort metric is how many vessels, gillnet vessels there are in the fishery, then question for you, and I'll actually give you like 30 seconds to think about it and respond a little bit in the chat, is how would you then go about getting a bycatch estimate if you've measured BPUE in gillnets per set and the fishing effort metric you have is number of vessels per fishery? So think about that and go ahead and type a few responses. Or Tessa, feel free to solicit a verbal response in the room if you want to moderate that.
Who wants to answer? Anybody have a guess about we have everything we need or something missing? What's the missing link? Yeah, in the back.
I could guess the average number of sets per vessel per season with some measure of variance. So you could do a sensitivity analysis.
Yeah, exactly. So you'd have to undertake some other type of estimation study and that might be based on interviews or trying to implement a logbook study or something to come up with how many sets are made per vessel per year, and indeed with variance estimation around that. So excellent, and thank you, Tessa. I got your note reminding me that people in the room aren't on Zoom. So okay, that I will note it. Great, thanks. Okay. Okay, representative sampling. So Phil talked about this at length and can't emphasize it enough, right? So when we are going to embark on like an observer program study, it is massively important, to the extent feasible, that your sample of data essentially look like the fishery itself, right? And if we're implementing, so theoretically, and I say theoretically because we won't really be able to do this in practice in a fishery, but if we're able to randomly sample fishing effort units, so we were able to get a random sample of the gill net sets that took place in the fishery, for example, then as that sample size grows large, we can trust that that the expected value for that sample is going to approach the true value for the fishery. We can trust that our approach is unbiased. Representative sampling essentially means that all units in the population, so all fishing effort units, would have an equal probability of being sampled. And it's the basis for making design-based inference. With design-based difference, essentially what we're saying is we're treating a model as the model for the system as being known, and the emphasis is on carrying out a good field study, a good experimental design, good survey design, so that we can ensure the model assumptions are met, and then we know that our inference is valid and robust, that our approach is unbiased. Another important consideration in our sampling scheme is to consider what units are actually independent, right? So we recognize that a lot of fishing sets or trawl deployments or long line deployments and retrievals are going to occur within the same fishing trip, right? So all of those sets, let's say, are statistically related to each other in the sense that they're being conducted by the same fisher in a similar area in a similar time. So so the sets would not be independent units, but the trips might be. We might consider kind of the set of trips that are occurring within the fishery as being statistically independent units. So we might think about trying to the extent possible, sample a representative set of trips that are occurring in the fishery. And if we don't have independent units, then the analyses ultimately have to take this into account somehow. And we're not going to go into the details of that, but it's achieved by doing things like, defining covariates, assigning random effects to certain levels of the fishing units, or when we're doing like bootstrap resampling or something to come up with our variance estimates, doing the resampling at the level of those independent units. In reality, getting truly like random samples of fishing effort units is not something that's typically that feasible. And so what the focus, how would you know what the universe of fishing sets is going to be and randomly select which ones you're going to choose ahead of time. So the emphasis becomes on understanding the characteristics of the fishery as well as possible. And that often will require its own study before you actually get into the bycatch estimation part, really understanding where is the fishing effort occurring out of, what gears are being used, what vessel types, how many of them, when's the fishery operating, and then you can partition your fishery up into, okay, certain amount of the fishery occurs in this season, this season, this season, this area, this area, this area, certain, we have a certain number of vessel type A, a certain number of vessel type B, and we're going to try to sample each of those sort of cross factorial sets of variables, and thereby get as representative sample as possible of the whole fishery. Okay, so we are going to jump right into an R exercise. So go ahead and get your R open, get your R Studio open, have that R file open. Okay, so you should have yours open and it should look something like this. And the first exercise we're going to run through, I've tried to label this code pretty clearly. So you'll see example 1, and you'll see a bunch of code. And the first few lines of example 1 show a few parameters you can tinker with. So we're starting out with a fishery that has 1,000 sets that occur over time. And here's a parameter that, of course, you, the researcher, won't know, but the true latent parameter is that the probability of bycatch occurring in any particular set for like the year is 10%, 0.1. And you have put observers on 20% of the fishing effort. So 200 of the sets get observed. Okay. And so you guys are going to go ahead and implement line by line, execute your code. And I'm not going to walk you through every line, but what I want you to do is we've got these first few lines, so we can execute those. And then we're going to see what that looks like. So these next few codes should plot in space where all your fishing sets are occurring. And you could just be walking through this with me. And then you're all going to be doing your own experiment here. So bycatch is going to occur in some of those sets, and some of those sets are going to be observed.
Jeff?
Yes.
Would it help us to do a set seed so we're all seeing the same thing? Just at least in this stage.
What was the first part of your question, Andre?
Should we put in a set.seed so that we're all seeing the same picture as you when we run?
No, I'd rather you all have your own experiment.
Okay.
Trust the teacher.
I am the teacher.
So you'll see what your fishery looks like after a year of process has occurred. All right. So you'll be looking at your fishery and you'll see that the red dots are where are sets in which bycatch occurred, and the blue circles are sets that were observed. All right. And as you continue to execute a few of those lines of code, you will get down to this line, which is line 42 in the code that says obs.data, and that's the data. And you can look at what the data looks like real quick when you execute that line. So you'll see you've got a data frame there with the set numbers that were observed, their location in space, and that the one in the observer field that shows all those sets were observed, and in which of those sets bycatch occurred.
Can we just pause right
Okay,
here?
and then,
Yep.
Just to let people catch up. Some people are.
Yep, absolutely.
Pretty picture.
Absolutely.
Good. Anybody need?
Yeah, don't just use the run feature so that you can keep up with Jeff. If you hit source, you'll get a gazillion. That's just That's just editing, so keep hitting the run button.
Yeah, this is it.
So Tessa and Andre, I'm gonna wait for your cue to let me know when most people have,
Yeah, we're just gonna make sure
Okay.
everyone's in the same place.
We will let you know, so sometimes you're, well, sometimes, yeah, down here.
And I've got the thing on a stick as well. I'll be right back. Ooh. Yeah. No, I use RR Studio.
Yeah, but you need to.
Yeah, no, I'm just trying to step
Anybody else need assistance?
Well, we've got who uses R on a Mac? Why would you use R on a Mac? She does. Sorry? No, not me either. Sorry? Tessa doesn't.
Just execute the whole file.
This is what you're getting. But don't try to run separate model through R on a Mac because it doesn't work. We're not going to do that here. When I teach, it's like, okay, anyone in class on the Mac? Go get a new computer. We'll try it with the class. Ain't gonna work for you. But I'm assuming that you know how to get the step through the tool. Has everyone got little green pictures? I've got it on a stick as well. Oh.
how are we doing?
We're close, we're very close.
Yeah.
That's really good.
Yeah, I bought this computer because my people that are NGIS do not work well on PCs. So I had a Mac, and so I bought a PC.
Right, yeah. No. But yeah, if that doesn't work, I'll just give you a stick and you can just copy the file.
No, that's good. Question.
Oh, you've got two files.
Yeah.
Yes.
This is for
You would do some sort of restructuring.
Okay, and he's up to line
Yeah.
42, it looks like.
Okay.
Are you through line 42, Jeff? Is that right?
Yes, we are on line 42.
Okay, I think, are we good?
Okay, line 42, everyone should
I
just
think,
step through to 42.
I think we're good. Proceed,
Okay.
Jeff.
Okay, so at this point, you'll have a plot showing the map of your fishery, and you'll have and you can see your R data object called obs.data, which actually shows your observer data. So each row is a set that you observed, and then the last field in that table shows which ones had bycatch in them. And so now we just want to go about estimating our BPUE. And that is going to be, if you execute lines 45 and 46 of your code, you will get the total number of bycatch mortality events that were in the data set, and your estimate, which is the number of mortality events observed divided by the number of sets you observed. So you'll have however many bycatches there were, that's your obs.m, and your estimate of BPUE. And then if you execute line 50, that will actually...
Is there any way to get rid of the click to join so we can actually see what's the key number that we're supposed to compare with?
I'm sorry, what was that question again?
We were just trying to clean, right now, there's a box right on top of the answer. There we go.
Oh, for what you're seeing on the screen?
Yeah.
Sorry, I fixed it, I think.
Tessa has solved the problem.
Okay. Sorry, I don't see what you see, so I hope it's okay now.
It's perfect, thanks.
Okay. And then if you execute your line 50, that'll actually give you your bycatch estimate, where we have multiplied the BPUE estimate by the total number of sets in the fishery, which we've treated as known. So you all have a unique number right now because this is a random sampling process, and that's sort of the idea. And if you execute lines 53 and 54, you can just sort of side by side compare the true amount of bycatch in this fishery to what your estimate was. And just for Tessa and Andre, like show of hands, how many of you had for how many of you is your estimate above the true value? And then I'm assuming some hands are being raised now. And then for how many of you is your estimate below the true value? And hopefully it's about half and half.
Yeah.
Small sample.
Not significantly
More or
different.
less.
Yeah, it's close to half.
Okay. Okay. So, you know, this is a real simple exercise in sampling variance, right? So your estimation process is a random sample, and some of you are going to have by chance have sampled more sets that had bycatch in them than others. And based on that, your estimate is going to be above or below the true value. And if you, rather than all of you individually being the replicates for this experiment, you can now kind of run your own experiment to you can all each run your own multi-replicate experiment. So if you execute the code from lines 57 to just select the whole block of code from lines 57 to 68, and you execute that, you will do your own experiment of basically repeating a scientific observer program 1,000 times. And then when you execute line 71, you'll see what all those estimates look like. So I'm going to pause there and wait for Tessa and Andre to kind of let me know when it seems like people have successfully done that and are mostly looking at a histogram plot that shows along the x-axis the bycatch estimates, and then how many of your estimates fall within different bins. And there's a red vertical line there that shows the sort of long-term true value, and we're going to see what our estimates look like surrounding that true value.
Yeah, it is. I mean, I have the email. With all the, well, this is the cloud.
How are we doing?
Yes.
Yeah.
Are we pretty good?
Close, Jeff, very close.
Okay.
Well, yeah.
Yeah, I can't, yeah, I've never even, don't even know what the problem is.
Yeah. Well,
Right on the cloud.
yeah, you guys are welcome. Yeah.
Right on a living clock somewhere, you can see the limits direction. Okay, Instagram. You can't find the files.
I tried.
Okay, we're good, Jeff.
Okay. Okay, so hopefully you all have a histogram on your screen that looks something like the one that hopefully you can see on my screen. And, you know, just some things to kind of to take a look at with your histogram. So you have your true value. Hopefully your estimates are, your distribution of estimates is centered on the true value. That would indicate that our approach is an unbiased approach. So in the large sample, our expected value is converging on the true value. You can take a look at the variance, right? So you can see that based on the amount of observer coverage we had for a fishery of this size, and given the bycatch rate, what our variance of estimates looks like, right? So our expectation is that there were 100 animals caught in this fishery per year or whatever. But you can see that any given estimate you might have obtained from your observer program could have been anywhere between like 50 and 150, right? Or more, you know, most of the mass is maybe between 75 and 125. And that, depending on your management goals, on the conservation of status of the species, the population size of the species, that variance might be, that level of precision we have with this experiment might be adequate, or it might not. And so what I'm going to ask you to do for a few minutes is basically go back up to the top of your code and go to those lines 16, 17, and 18 where it says these are parameters you can play with. And we'll take a few minutes to do this. Go ahead and change some of those values. So imagine, and I'm not going to tell you which ones to change. You can all do your own thing. So maybe the fishery is bigger or smaller. So you only have 500 sets or 10,000 sets. Maybe the frequency of bycatch is higher or lower, or your observer coverage is higher or lower. Go ahead and tweak, I would say one value, because you want to investigate how that one thing affects your data. So tweak one of those values, rerun that line of code. So I'm going to do this. I'm going to say that I'm going to increase my observer coverage from 0.2 to 0.4. And I'm just going to rerun that line of code. And then what I'm going to do is scroll down to line 57, where I had the loop of code, and I'm going to rerun that experiment and plot a new histogram. And I'm gonna see how my estimates changed when I did that. And I want you all to do the same thing, but vary something else, vary something of your own, and explore how that changes your distribution. And kind of make a note, like what, like how the precision essentially of your estimate changes depending on the size of the fishery, or the amount of observer coverage, or what the bycatch rate is. And we just take a few minutes to do that. Go ahead. And then as before, Tessa, Andre, let me know when it seems like people have had a chance to kind of do that.
Okay.
So Jeff, there was a really interesting result here. What is the
I'm listening.
I'm just looking. This histogram was sufficiently interesting that you might want to reproduce it. Change the true proportion to 0.01 and recreate your histogram.
Yeah. So actually, you've touched on the next topic.
Okay, so don't do that.
So hold on to that result because it is interesting and important. So, and we're going to talk about the cases of very low observer coverage in a second. But in general, does it look like people have had a chance to rerun through that exercise?
Yep. I think.
Okay, very good. So in my case, I doubled my observer coverage, and my histogram is, my estimates are a lot more precise now. So rather than my histogram ranging from 50 to 150, most of my estimates are between 80 and 120. And so not surprisingly, higher observer coverage, all else being equal, I get a more precise result. Okay. I'm going to come off of R for a second and go back to my PowerPoint. Okay, and we are going to talk about the problem of rare events. Okay. And this topic's discussed really nicely in one of the papers in our special topic issue, the Biennial et al. 21. So rare event bycatch is not uncommon, and so we might have a situation where, given the size of the fishery or the relative rarity of the population size, bycatch might not occur that much in our fishery. So maybe, for example, we have a small population that we're concerned about. There's only a couple hundred animals. And we're concerned that if there's just a small handful of catches per year, that could be a conservation issue. But if there's only a few catches per year, and we don't have much observer coverage, then what's the chance that we're going to even detect that bycatch, that important, albeit rare, but important bycatch is occurring? And so what we're going to do now is go right back to back up, and if you go to line 80 real quick, you'll see it says example 2, exploring rare event small sample problems. And there's a little bit of an assignment here. Which basically says, go back up to those parameters you can play with, but use very small values for BPUE and observer coverage. So you might, example, you might set both of those to 0.02. So we're only observing 2% of the fishery. So 20, we observe 20 out of the 1,000 sets. And bycatch itself is not occurring that much. It's just a couple animals, or not that many animals per year, and we don't observe that much. So go change those values to 0.02, or you could even make them like 0.01 or 0.03, somewhere in that neighborhood. And then rerun that loop of code. You don't have to run everything in between, but change the values up there at lines 16, 17, 18, and then rerun that loop of code that's down at lines 57 to 71, and see what your histogram looks like after you do that.
Sure.
We're getting some audible wows in the room. Jen.
And just kind of give some thumbs up when you've got your plots created.
You're very sad.
Thumbs up?
Thumbs up.
Thumbs up. Okay. So your histograms are not wrong. What happens in this kind of situation is that in most of your experiments, you're going to have 0 observed catches in your observer program, right? So only a handful of animals got caught. Actually, for the value I used, the 0.02, like 20 animals got caught, but we didn't observe that many sets. And so most of the time you observe 0 animals caught in your fishery. And if you apply the simple estimators that we've talked about so far, your estimate will therefore be 0. So you have a large bar in your histogram of where your estimates are 0. Occasionally, you will observe 1 or a couple of those catches. So now by chance, you observed 1 animal and your observer coverage was 2%. And so you multiply your 1 animal caught, you divide that by your 2% observer coverage, and your estimate's 50. So in this particular kind of situation, you can never get an accurate estimate. You're either gonna estimate 0 animals, or you're gonna estimate a lot of animals if you happen to observe 1. So you're either underestimating severely, or you're overestimating severely. And this is this is like what we refer to as, the rare event problem. And I'm going to go back to my slides. We're going to talk about that for a sec. Okay, so how do we deal with this? Well, okay, one thing is a little bit of a no-brainer, right? Is we need bigger samples. And a lot of times the way that is achieved, if you can't get a greater sample size like in a given year, is to start pooling your data across years. So maybe over the course of, in that 1 year you observed, only 20 sets, but after 4 or 5 years of data, you've observed 100 sets, and you're more likely to have to be getting out of the small sample case that you're in, and you start getting a little bit better estimates. And then there are other inferential approaches that can be taken. Bayesian inference kind of gets you out of this problem. There's some machine learning based methods that have been applied to this, and others. Again, I would say take a look at that Janot paper for different ways of dealing with this rare event case. But it's basically something to be mindful of, and we're going to explore this more deeply using another tool, which is developed by a couple people in my group. And the tool is called Observer Coverage Tools, OBSCOV tools for short. So we're all going to go to this website that you can see on my screen. If you don't have that opened up yet, it's...
Hold on.
Yep.
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 Yes. People who can't download things should be able to get to them.
Yes.
People are really enjoying this because you can all get to the website. Okay, anybody not on the website?
Hooray. Okay, very good. This tool is.
It's a lot easier when you're in the room because you can see.
I lost all my like homework.
Okay, are we all caught up with this?
Yeah.
Everybody ready? Okay, yeah, go for it.
Okay. Great. Thank you, Andre. Thanks, Tessa. Glad you're there. Thanks for shepherding the process. Yeah, okay. And you guys see my PowerPoint, right? Okay. This tool is well documented in this article, Curtis and Coretta 2020 in Fisheries Research. And there are 3 modules to this tool. So I just have a screenshot on my slides of the first module that we're going to play with for a little bit. And what this tool, this particular module is for asking the question, if there is bycatch in my fishery, how much observer coverage do I need to have? And observer coverage, I've been using that phrase a bit. We're talking about the proportion of fishing effort units that are observed or that we have data for, you know, if that's from interviews or logbooks or whatever. What proportion of the fishery needs to be observed so that if there is bycatch in the fishery, I have a certain level of confidence in detecting it with my observer program. Okay, so the default entries, when you open this tool, you'll see here's the total amount of effort in your fishery. So the default in there is that there's 500 trips or whatever. And there's a bycatch rate. So there's your BPUE. And that's, of course, not something that's going to be known to you. But let's say, just to use the defaults that are in here right now, let's say I know I have 500 trips in my 500 fishing trips in the fish per year in this fishery, and maybe I'm concerned about bycatch being 5 animals or more. So I would put in this value of 0.01 because that would correspond to 5 animals. The effort's 500 set, 500 trips. And if 1 animal per trip were caught, there would be 5 animals caught in this fishery per year on average, right? So I put in a value that maybe corresponds to a value I'm concerned about. This next field, dispersion index, we're going to leave that at 2, but it's essentially a variance inflation factor that, you know, if the bycatch process is, let's say, over dispersed compared to like a Poisson assumption, we could put in different values to reflect that. And let's say and again, just looking at what's here on my screen already, that last field, there's that sliding bar down at the bottom that currently says, I want to have a pretty high confidence that if there's bycatch in the fishery, I'll detect it. I want to be 95% sure that if there's bycatch in the fishery, I would detect it. And so given the values that are in these fields right now, the graph is showing you how as observer coverage increases along the x-axis, your probability of detecting bycatch changes, right? So as your observer coverage goes up, your probability of detecting bycatch goes up. That's what those increasing curves are showing. The horizontal lines up at the top, and I'll explain the difference between the solid and the dashed lines in a second, but the horizontal lines at the top are showing you the bycatch. Given the BPUE and given the effort in the fishery, those horizontal lines are the probability that bycatch occurs in the fishery. Okay. actually more specifically, the black dotted line is the probability that it occurs in the fishery, and the red dotted line is the probability that it occurs in your target coverage, given that there was a bycatch event in the fishery. So it's a marginal probability and then a conditional probability. One is the marginal probability that it occurs in the fishery at all, and then one is the is your target coverage given that bycatch is 0. So you can see, if we look at these curved lines, with what's showing in the default, that if you want to have a 95% chance of observing bycatch in this fishery, you would need, given the effort and given the BPUE, you would need to have about 75% observer coverage. And that's actually summarized in the text below. So this graph is kind of summarized as a little text description. So for what we're seeing here, probability that any bycatch occurs in the effort at all is 97%. And you would need 73% of your trips to be observed to have a very high probability of detecting that bycatch. So go ahead and play with that for,
Do you want me to repeat it again?
go ahead. Yes. Are there, yes, questions? Yes, questions. Thank you.
No, everyone knows, the only one who's stupid enough,
Okay.
that is me, you're fine.
Okay. So here are some questions. So here's a question. Here's a problem for you to work on. So you're conducting fisheries management for a small endangered population, and the best estimate of your population size is 100 animals. So annual bycatch of just 2 would be considered a conservation concern. But you don't know whether bycatch actually occurs in this small gillnet fishery that you manage. And so you decide to establish an observer program to learn more about the problem. There's 50 vessels in your fleet, and each vessel makes about 20 fishing trips per year. So how much observer coverage would you need? That is to say, how many of the trips, what percentage of the trips would you need to observe to have 90% confidence that you're detecting bycatch in this fishery, if 2 bycatches per year are in fact occurring? Go ahead and work on that for a few minutes.
How many trips were there?
20 trips a year, 50 fishing vessels. Oh. Anybody else having difficulty accessing the page?
Oh, really?
No?
Have you never been on it? Oh, maybe you don't have the address right.
Check that you have HTTPS.
I just,
Yeah.
we may have maxed out of,
Is it a max thing? No.
no, it's saying it can't handle us. I'll get off.
Okay, so it might be that only so many people can really access that server at once. If that's the case, I would suggest, I don't know, maybe a few of you can, maybe you can group up into groups of a few
I'm not
people
on
each.
the way.
Okay. Try again, I hopped off, maybe I made space for you. I know. All right, we created space, Jeff.
Okay.
Okay, if you're not getting on Huddle, basically, work in pairs. Oh, we're back on.
Yeah, she got my spot.
Yeah, it sounds like there's a quality of. Jeff, you've never had this much attention on this website before. Is everybody on, or at least sitting next to someone is
I see
on.
people working the problem.
Problem one, we got it under control. Hope so.
Am I in your way? Sorry. People are working through the problem, Jeff.
I think we've got, everyone's got an answer. That I can see.
Everyone's got an answer. Okay, very good. So I would like to maybe get a, what's that?
Part one. I think everyone's looking at part. Do you want to go through part one first?
Nobody catches that half of what we say.
What I would like to know as people get to the end of the exercise is what level of observer coverage did you come up with as being required to meet your to meet the goals and stated in question one here. What observer coverage level did you come up with?
Anyone want to throw out?
80% I'm hearing on this side of the room. 80% this side of the room and that side of the room. They're not willing to comment.
Anybody get a different estimate than 80% for the required coverage?
Sounds like 80%.
Okay, so about 80% is correct, and if you look in the text summary below the plot, it'll give you the more precise answer, which is 82%. Okay, so well done. Okay, so now the second part of this question. So your budget is.
First, Jeff,
Yep.
can you tell people the answers to the cells that they needed to fill in properly, right? Because that was actually.
Yeah, thank you. Yep. You guys are great for keeping me on track here. So yes, so total effort in the fishery, there were 50 vessels and 20 trips. So that's 100 trips per year. So you should have 100 in your top field.
No, that's 1,000.
Sorry. Yeah, right. Yep. Thank you. Yep. Thank you. Very good. Wait, 50. Yeah. 50 vessels, 20 trips per year. Yep. 1,000, right? Very good. Okay. So then, so yeah, I did typo. So then for your bycatch, you're concerned about there being a couple catches, right? So that's going to be a rate of 0.002, right? So there's going to be 2 animals per 1,000 trips, right? So if you have 0.002 in your second field, and then we're leaving the third field at 2, and then your bar down at the bottom would be 90, okay? And then you'll get your plot, and it will show in the text 81% of the sets would need to be observed. So heads nodding, thumbs up. Is that agreeing with people who said 80?
And Jeff, can you, there's a request to share your screen on the website, not the PowerPoint, if possible.
Yes, okay. Hang on a second.
Thank you. Okay.
There you go.
We're caught up, Jeff. You can move on.
.002.
Oh, now Jeff, we can't hear you all of a sudden.
So 1,000.00.
Jeff, you're muted.
Okay, you should be back now, Jeff.
Can you hear me now?
Yes, thank you.
Okay, for some reason, it muted me when I went to that website. So
Weird.
yeah, but I think that's okay. So your budget's only 50% of what you need to get that observer coverage. Okay, so you're going to observe what you can, which is half of what you need. So now, what is the probability that you will observe bycatch in the fishery? So go ahead and adjust your tools to try to find that answer.
So can you put the PowerPoint back up now, Jeff? Sorry, that way we can see the question.
Yes,
Sorry.
we're bungling through it. You see it? You see the PowerPoint now?
It's perfect, thank you.
Okay.
We're getting some answers here. Jeff,
Yes.
you said you got to change the tool. We think we just have to read it off the graph.
Indeed.
All right, so there's no changes to input. You should just be drawing your finger on the screen. Probably not.
Well, you can scroll that far though.
But what you can do, Andre and everybody, is so you can scroll on the screen, but then you can also, as you move the tab, as you move the sliding tool, that red horizontal line and your star will move down. So slide the tool until you.
I think it would help if you went back to R for this.
To R?
To the website.
Well, but it mutes him.
Oh, well then we don't.
That's okay. That's okay. I can be muted for a second, and you're gonna watch me slide the bar, and see what happens there.
Okay. Slider is the thing we're going to be playing with here, I think. So there he is. He's moving the slider so that, and watching the effort go down till he hits 40%. So the red dot is right above 40. I hope.
Yeah.
And then you can read across at what, 57%, I think.
Yep.
Excellent. Did everybody see how that worked?
Yeah.
Personally, just reading it vertically worked.
It is pretty sad though, with 40% coverage, you're only seeing.
Okay. So what you should have seen. So I slid the bar down until the red star was over about 40% observer coverage. And so now we can see that the probability of observing, if there is bycatch in the fishery, if bycatch does occur in the fishery, we could see that the bar is at about 57. So I would have about a 57% chance of observing that if some bycatch is occurring in the fishery. And then the dotted line is the marginal probability. So remember, given that this bycatch is a rare event scenario, it might not actually even occur in a given year. So the dotted bar, the dotted curve is sorry, I don't want to misspeak here. So the red line is showing the probability that bycatch occurs in my fishing effort, given that bycatch did occur in the fishery. Okay, so I'll say that again. The red line is this conditional ability that bycatch is in my observer coverage. Okay, and then the horizontal line, the dotted horizontal line, is the probability that bycatch occurs in the fishery at all. Okay, so there's about a 75% chance that bycatch occurred in the fishery. There's about a 58% chance that it occurs in my target coverage, given that there was bycatch in the fishery. Okay, and then again, those curves are showing how my probability of observing these things is increasing with my observer coverage. So are we good on that part for now?
Thumbs up?
Thumbs up. Okay, great. We're going to talk about the second tab. Are we seeing my slides right now? I can't remember what I'm. No, let me share my slide. Let me share my slides. Okay. We do our observer program and we didn't catch any, and then there wasn't anything. So this tool is giving us some information about how much bycatch might have actually occurred in the fishery, given that we didn't see anything. Okay, so this is obviously sorry, I shouldn't say obviously. This is a purely statistical concept, right? We might know that the animal population doesn't overlap with the fishery. And so in that case, we don't see any bycatch, and we feel pretty comfortable that there wasn't any bycatch because we actually know something about where the animals exist. But let's say we truly don't know anything. Okay, I've just landed on Earth. I don't know what cetaceans are. I go out, but for some reason I know something about observer programs. So I go out and I collect some observer data, and I don't catch anything for mammals. Okay, statistically, I could ask how high might bycatch have been given that I didn't observe anything? Because obviously, just because I didn't observe it doesn't necessarily mean there wasn't any. It just means I didn't observe it. And this tool allows you to explore that. So again, we're going to leave that dispersion index alone for the time being. But we can play with the amount of effort in the fishery. And we can also, so that's your top field. And we can also play with defining the confidence limit bound. So what's the default in this bar that you're seeing is to quantify your upper 95% confidence interval. But you could change that if you felt so inclined, but you could change that. And what you see in the plot is what your upper confidence limit for bycatch might be, given that you had the amount of observer coverage that's described on the x-axis, and given that you didn't observe anything. So notice how this sigmoidal shape declines in this S-shaped fashion and approaches 0 if your observer coverage is close to 100%, right? So if you observe the entire fishery and you didn't see any marine mammals in your observer data, again, you observe the entire fishery, then you can be pretty darn sure that your upper confidence limit for bycatch was in fact 0. But if you observed close to 0% of the fishery, then your upper confidence limit for bycatch is something quite high, right? You really have no idea how high bycatch could be if you observed almost none of the fishery. And then as you observe more of the fishery, that upper confidence.
Shoot.
Oh, now it's back.
Yeah, it's fairly straightforward, I think. So I'm going to show you. I hope so. I hope it's straightforward. So we're going to, I got a couple questions here for you. And it's related to the prior problem. So you observe the fishery at the level you could afford. Okay, so that was the, what, 40% observer coverage, right? And you did not observe any bycatch. And you can use the effort, that we had in that last slide. So I think there were 1,000 trips in that fishery, right? In problem 1, there were 1,000 trips in the fishery. And you have about 40% observer coverage. So how confident are you, just sort of qualitatively speaking, that there really was no bycatch? Okay, so I'll leave that as rhetorical for a minute, but just think about that for 15 seconds. And then, given that you did not observe any bycatch, again, with your 40% observer coverage and your 1,000 sets in the fishery, what is the upper bound for how much bycatch might have actually observed? So I'll give you a minute to kind of do that, think about that, maybe, you know, mutter your answers to André and Tessa, see what you guys get.
So 95% probability, and we want to know for 40% coverage, what our message. No, what we say every 40% coverage, the upper 95, and you observe nothing, right? Well, upper 95% confidence interval can still be kept. Okay, so if you see, sort of, you know, normally when you present results, you give an estimate and a confidence interval, right? The estimate is obviously 0, it's actually a good confidence interval from 0 to 10. So, but the way he's expressing is actually thinking Bayesian, but really this is a, it's saying the confidence interval would go all the way to 10. You observe 0. So think of a confidence interval that starts, you know, the best estimate is 0, the lower confidence interval obviously is 0, and the upper is 10.
So what do we think?
Thing to be aware of is that the best estimate being 0 doesn't exclude anything.
Who's got some 8?
So what do we think?
8.38, someone's really precise. I need a third decimal place for someone.
I'm good with approximations.
Yep.
What do we think?
10.
About 10.
About 10. Anybody got something different?
Yeah, well, 100% confidence isn't the top.
So if you were getting about 10, you're in good shape. If you're getting something substantially different from that, you could raise your hand and we could talk about it.
Jeff, there was a really interesting point that was made, and you might want to expand on it, which is if your manager comes to you and says, I want to be 100% confident, why does it crash? Go to 100% and see what happens. So my manager would be really upset. They want to be really certain, right? So why doesn't it work?
Nothing.
Well, I'm sorry, I'm not hearing the question very well, Andre.
The question is, what if the manager wants to be absolutely certain? Why does the 100% confidence interval work in the software? I want to be 100% certain. Why do I have to be 95% certain?
100% I'm certain. Go observe every vessel in the fleet.
Yeah, but I only want to observe 40% and be 100% certain of the upper bound. No?
You can wish that. I wish I could fly.
Jeff, I'm just going to give you a time check. We're at 5 minutes before.
Yep, very good. That's, yeah, our timing's good. We're going to try to get through the third module. Actually, I'm going to ask this final question. So let's suppose what you really want to make sure about is that bycatch isn't more than 3 animals. So first, given the population size, 3 animals is 3 or more animals you've decided is something to be concerned about from a conservation perspective. So there's this field here, target maximum UCL, given 0 bycatch observed. It's the field right under the sliding bar. And if you enter a sort of a target, a threshold level of bycatch that you're particularly concerned about, and what you're essentially telling the program here is like, let's say that this is, let's say bycatch is at this level, okay? The true bycatch in the fishery is at this level. Then how much observer coverage do you need to feel confident that the true bycatch was less than or equal to this? So you could put in 3, okay? And a red horizontal bar will appear, and it will tell you if you want to have high confidence in my, 95% UCL, let's say, whatever level you state. If you want to have a certain level of confidence of detecting, of making sure that your bycatch isn't higher than that, then you would need, in this case, using 3 in that bar, it would say you need 74% observer coverage to make sure that you're, that if you observe none, you can be confident that there are in fact 3 or fewer. Does that make sense? The way I stated that.
And everybody got it, yeah.
Okay. The last, we're going to go to module 3, and this module 3 is, you'll see your fields on the left side of the screen. You won't see a graph yet because a simulation is going to have to occur under the hood, and it doesn't take that long depending on how large the fishery is, how many fishing effort units are in this fishery. And this is a module you would use if you want to identify how much observer coverage you should have to estimate bycatch with a certain level of precision. So all you have to state in here is the size of the fishery. So put in whatever you want. Don't make it too large, because the larger the number, the longer the simulation takes. So keep it on the order of like something less than 10,000. You put in your BPUE. So again, this is conditional on the true BPUE being something that maybe you've estimated from a pilot study, or maybe it's just a level of BPUE that you're concerned about. And once you have your fishery effort and your BPUE, you just hit submit, and it takes, and you'll see a little like a little time bar on the right side if it's working, that will show you that it's running. And this might be something that will be problematic for the number of people trying to do this, because it's actually not running for me right now, which is like never happens. So is it running for anybody, Andre?
I'm getting lots of, one person.
Oh, they were the first in.
One group grabbed the server.
Okay, so maybe it'll be sort of a one at a time, or maybe just 5 or 10 of you do it. Keep your fishing effort units small, maybe like 1,000, so the simulation runs quickly. And let's see if we can get a few people to get that running. And in the meantime, I'm gonna share, you guys see my PowerPoint still, right?
Yeah.
Okay, so you'll get a graph that looks like this. And if we're not getting our own, you can just look at mine.
I think we can look at yours.
Can you maybe zoom in one level?
Yeah, you bet.
He's gonna switch to a different.
Better?
That's lovely, thank you.
Okay, so you'll get a plot that looks like this, okay? So what this is showing is that as your observer coverage increases to the right, the CV that you could expect from the CV of your bycatch estimate will decrease given the parameters you've input. So given the size of the fishery and a certain BPUE, these are the CVs that you could expect associated with your estimates. And then the intersection says if you want to have, it uses as a default for the intersection a CV of 0.3. So this says if you want a CV of 0.3, CVs are on your y-axis, you would need 81% observer coverage, given, you know, given the size of the fishery and the BPUE. If you increase your fishing efforts, if you increase the size of the fishery, or if you increase your BPUE, this is actually something you play with on the break, because I know it's time for your break. But you could explore how changing the size of the fishery, changing the BPUE, changes the CV. And I'll give you a little, I'll just kind of cheat because of time. Essentially, your CV is going to be related to your sample size in terms of number of animals caught in the fleet. So either as your BPUE goes up or as your fishing effort goes up, so that you're getting more positive bycatch events in your data set, that will drive your CVs down. And if you want, you can play with different values of effort in the fishery and BPUE and see how that changes the observer coverage required to get certain CV levels. And that pretty well covers this block. So I think we did pretty well. We didn't get to go through the last exercise, the questions to you guys to do on your own on this last slide, but otherwise we got through everything that I'd intended before lunch.
I'm feeling a little silly, but can you explain what CV is?
Yeah, your coefficient of variation. It's a ratio of your standard error to your estimate.
Okay, thank you.
So it's a way that we quantify that we communicate variance of our estimate.
Okay, awesome. Good job, Jeff. Thank you. Well done with all the different tools and everything.
It actually worked.
Great. So people don't want to tear themselves away from the tool, Jeff. This is good. People are into it. Cool. So we are now on a lunch break until 1 o'clock. The room will stay open, but I would take your stuff with you if you leave. Yeah, we'll see you back here at 1 o'clock.
Yeah, and given how well the server has
Move into the new stuff after that. So the question.
This meeting is being recorded.
So the question that got posed to me during the break by Kristy was if we want to determine whether bycatch exceeds PBR, and I think we could replace that for general purposes with, exceeding some value of concern, some reference point, some threshold, whatever. Which part of the the observer coverage tool would we use? Especially like if we don't know BPUE. So I would say, first of all, that's not that question, at least as it was framed, determining whether bycatch exceeds a certain level. Can we determine whether bycatch exceeds a certain level with this tool is not what the tool is designed for. But the tool is designed to say how much observer coverage would we need to use to ensure that we can properly evaluate that question. So like if I share my screen again and I go to our PowerPoint, you see my PowerPoint? Yes? Okay. So here I'm on the third tab where we're talking about maybe wanting to achieve a certain CV. And we know that, and our concern is that, maybe we know the size of our fleet, it's 1,000 fishing effort units, and our PBR or reference point is like 10 animals, right? So then we would use a BPUE so that BPUE times effort gives you 10, right? So that's what we would use for BPUE. and then we could play with our observer coverage. Or similarly, if we look at like this tab, maybe it's a rare event kind of situation, the PBR is small, we could play with this value and say, you know, given 1,000 effort units, and we're concerned about a bycatch of like 2, so we would use like 0.02 or whatever, and then we could say, what observer coverage do we need to have a high probability of detecting bycatch in that kind of situation? So just making sure we're kind of framing the question correctly. Kristy, does that address that question?
Yeah, and like ultimately, the reason why I'm curious is wanting to do an assessment of how much observer coverage do you actually need in your fisheries to observe some of these rare events, and trying to sort of balance that out with trade-offs in terms of CV and all those other things when resources are obviously limited.
Yeah.
So I did leave out that key part of the question about how much observer coverage do you need, but that was what I was really after, so good job.
Okay.
Jeff, I mean, your calculation is presence of bycatch. I mean, somewhere underneath there is a negative binomial, I'm pretty sure.
Yeah, that's what the dispersion index is in here is for. Yeah.
Right. I mean, I would have thought almost a combination of tools 2 and 3 is what you really want, which is what level of coverage do you need? Not that you get a non-zero number, but that the true bycatch is at least the PBR, basically. Can we be certain that the lower 95% confidence interval is less than 10 if that was PBR, basically? So I think this would be the tool I would use to ask that question. I'm not.
Okay. I feel like I need to move on to our next segment.
Thank you.
Okay, so we're going to be talking about non-representative sampling now, non-representative sampling or potential non-representative sampling and how we deal with that. Okay, so essentially with non-representative sampling, we're dealing with a situation where the data we have, so information about observed fishing effort units, is not representative of the fishery as a whole. And that can happen for a whole bunch of reasons. Sampling a fishery is a messy endeavor, right? We don't just have access to like the universe of fishing effort units that occur and know what those are going to be ahead of time and be able to sample whichever ones we want. The sampling process we undertake is often going to be highly constrained by where we can sample and when, and which fishermen are willing to work with you, and all sorts of things. And so we might sample more heavily in one part of the year than another, even though the fishery is occurring, even effort year round, but we're not sampling it that way. Or we're sampling more heavily in a certain geographic area that we can more easily access. We're sampling different types of vessels and gears in disproportion to how they're being carried out in the fishery. Maybe one type of vessel can take observers and another type of vessel is too small to take observers. All sorts of reasons that our data might not be sort of the microcosm of the fishery that we want it to be. And this can result in substantial estimation bias if bycatch per unit effort varies with respect to these factors. Okay. If BPUE doesn't vary with respect to those factors, it's the same in season A as in season B and in geographic area and in B, then it doesn't matter so much whether your sample is conforming to those two factors that I just mentioned. But typically BPV will vary with some factors, and it's important that we're trying to sample representatively, but we might not. So we're going to dig right back into R. So we're going to open up our R Studio. You can see my R screen, I hope. Okay. So we're going to work through this initial example together. Sorry. Okay. So we're at example 3A. So you're at line 95 in the code. Okay. And we're going to explore a simple case where we have an area A and an area B in the fishery, or it might be a time frame A and a time frame B, or fishing gear type A and fishing gear type B. But let's just contemplate it, and for the thought experiment, let's say it's two different areas. And in those two different areas, we have a certain number of sets that are conducted, and we have underlying bycatch rates that are occurring in those areas. And there's two different rates in our example for the two areas. And our observer coverage is different in those areas as well. So we're not sampling in proportion to the amount of effort that's occurring. We're sampling a different proportion of the sets in fisheries A and B. Maybe area B is a lot easier to get to, and the fishermen are more cooperative, and so we go out on a lot more fishing trips in that stratum. So we're gonna highlight that code and run it. So those are just our input parameters that we can play with as the user. And we're gonna take a look at we're gonna see what this fishery looks like. So you're gonna highlight that next block of code, lines 107 to 112. And we're gonna look at the distribution of fishing sets. That's not yet showing where bycatch is occurring and so on. We'll get there in a sec. But we've collected our data. So that's this block of code, lines 115 to 20. You can run that code.
So can I just ask Jeff, just for clarification? So
Yes.
Is area A the top half of that figure then?
It's actually the bottom half. Thanks for asking.
Okay.
Okay. And there's a little comment here that says A is in the south, B is in the north. And we can run those two lines of code, lines 123 and 124, and see our data. And my plot's very compressed for this presentation. Hopefully yours is a bit more expanded and the dots aren't all quite on top of each other so much. And you can see our sets where bycatch is occurring, the red. Go ahead.
124, no, just pausing in the room.
Okay.
As long as you get through lines 124, then you should see red and blue on top.
Or 125 and 26.
If you've made notes.
Oh, yeah.
Change your line numbers.
I see lots of blues and reds and things.
Okay. Hey, Jeff, thanks.
Okay. So if we look at the data visually, we see we have two fisheries strata, and you can see visually, hopefully it's fairly evident, that there's a bit more bycatch occurring in the southern stratum A. But we've done most of our sampling in stratum B. And we're going to now explore what happens if we ignore that for purposes of conducting our estimation, right? So we just say, hey, we went out and we observed a certain number of sets in our study area, and we're assuming that we've representatively sampled the fishery, maybe because you think you have, or maybe because you know that you sampled more in some area than another, but you like don't think that's a problem. Maybe you're assuming the bycatch rate is the same throughout the whole study area, so you're assuming that's not a problem. Or maybe you're assuming that you've done more sampling out of what you think is like the more important fishing port. Like this is where most of the fishing occurs, and we think this is where most of the bycatch is occurring, so we've sampled this area more heavily. But you haven't taken that into account into how you do your analysis. So you repeat your BPUE estimation exercise like we did earlier. So we're gonna run a few more lines of code. We're gonna run lines 127, 28, 29, just those next 3 lines, where we've quantified from our observer data set how many sets we observed, okay? So we have the sets observed in area A, we have the sets observed in area B, and the total sets that we've observed. And we're gonna estimate our BPUE as the sum of bycatch events that we recorded across the whole data set. Okay, so first of all, this line 132 is the true bycatch, okay? So line 132, true M, that's the true underlying value that we don't know. But now we have our observer data, that's line 135. Go ahead and kind of run these as I talk through them. And then we quantify our total number of sets observed, and we quantify our BPUE estimate as the total number of bycatch events observed divided by the total bycatch, divided by the number of, let me restate that. We quantify our BPUE, we estimate our BPUE as the number of bycatch events that we recorded in our observer data set divided by the number of sets that we observed. And so we get an estimate for BPUE hat, that's line 139 now. And then we expand that BPUE estimate to the size of the entire fishery. That's line 143, and you can run that. And you get an estimate. And you can, if you run lines 146 and 147, you get a direct comparison of the true value to your estimate. And quick show of hands, is your estimate M hat over or under? How many of you have your M hat estimate under the true value? And then André, Tessa, you can just relay that to me. Like, is it most or a minority?
Most.
Most, okay, so most of you have underestimated the true bycatch value. And if you explore this on your own, so you run the next block of code, lines 150 to 169. So we repeat the observer program experiment 1,000 times, and we plot the distribution of our estimates. You should see something that looks like this. And so the question for you to answer, we'll do this rhetorically, is does your distribution of estimates contain the true value? But is it centered on the true value? Is it, has our approach been biased or unbiased? And do we think that that original estimate you got, where for most of you it was under the true value, do you think that was a sampling error issue due to like the random sampling process, or was it more driven, or at least partly driven, by a bias in our estimation approach? And you can kind of mutter a few answers to André and Tessa, and see what you think about.
Do most people's histograms look like this? Yeah, so most people got a histogram that looks like yours. And why do you think Do we think it's because of bias in the estimation or variance? Or sampling variation?
Remember, Phil had those 4 categories of imprecise, and this is his category 3, the bad one, where you think you know what the answer is with high precision, but it's the wrong answer.
Indeed. You would publish a value that says we're quite confident that the true value is below, let's say, 250, and you'd be wrong. So okay, so how do we deal with a fishery that is essentially heterogeneous with respect to when and where and how the fishing is occurring? So one robust approach to take is to take a stratified sampling approach. Let me go back to my slides for a second. So we'll talk about that for a moment. So stratified sampling essentially refers to like partitioning our survey into a number of different quote unquote strata, where the population within those strata are relatively homogeneous compared to the level of homogeneity of the sample as a whole, right? So if you think about a huge study area where there's fishing effort occurring in a few different areas and over different times, like there's a lot of variance throughout the fishery with respect to how, when, where, how fishing is occurring. And quite possibly, therefore, when, where, how bycatch is occurring. But if we can define different strata such that within that strata, the fishing is sort of similar, right? So think of a stratum as being the fishing that's occurring using certain methods in a certain area at a certain place in time. Then we might be able to count on the processes and the bycatch rates in that strata being relatively homogeneous compared to the population or large sample as a whole. And so what we essentially do there is we partition our data, we partition the fishery into these strata. We sample each of those strata. We try to implement representative sampling within those strata so that your sample for the stratum is representative, is like the microcosm of the fishery in that stratum. And then essentially we apply, there's different ways to go about your estimation in stratified designs, but you could think conceptually as we're essentially coming up with separate estimates for each of those strata and adding those all up together. And then depending on how much sampling occurred in the different areas, we have to take some weightings into account to get the variance right. But in terms of like a point estimate, we're basically summing up estimates from all the individual strata. Importantly, we want to try to define those strata before we collect the data. And this is where like pilot studies can be really useful. If we don't already have a good characterization of the fishery, we do a study before we start doing observer studies to get a handle on when, where, how the fishery is occurring. And we try to divide the fishery up into chunks where that we then design a sampling program for. There are many examples of post-survey stratification where we already have a bunch of data. We didn't have a sense ahead of time of how the system is stratified, or we're using a data set that someone else collected 10 years ago. And in order to deal with some non-representative sampling issues, we are trying in a post hoc way to define strata. Many examples of that, because it's just a real world problem conundrum of inheriting other data sets, trying to make the most of pre-existing data sets, or doing a sampling scheme before we really understand the characteristics of what we're studying. That can be done, but the the success, if you will, of doing that often depends on rather complicated statistical methods. There is no guarantee that you're going to have good statistical properties in terms of, because you might not achieve representative sampling in the strata themselves. And a lot of times there's not a good way of knowing what your biases are, right? So that's kind of a key distinction between like design-based approaches and model-based approaches. Is in like design-based approaches, you already know all the assumptions and you know the model, and all the effort is putting into collecting the data in a way that it conforms to the assumptions in the model. But if you already have the data first, and then you're kind of trying to define the model, you'll get your estimates and you won't really know if your assumptions were met, or if they weren't met, what the consequences are of that. So there's, fancy analytical methods and statistics are frequently a way of dealing with problematic data. And the better you can do your study at the outset, the simpler the methods, which is always a plus, and the more reliable your results will tend to be. Let's see. So next slide here. Okay, benefits of stratified sampling. One is that it helps ensure representativeness of a population sample, especially in small sample cases. So if you imagine you have a big fishery that you don't stratify, and you're able to achieve a random sample of fishing effort units throughout that whole fishery, but your sample is not large, there might be important aspects of the fishery that are missed, that do not get included in your sample just by random chance. But if you're able to stratify your data ahead of time, so for example, maybe most of the fishing occurs in area A, but a little bit of fishing occurs in area B, and you think the bycatch rate could be high and it could be important. Okay, if you stratify to A and B, then you ensure that you get a sample from B, if that makes sense. Whereas if we just like do one big random sampling process, you might not get any samples from area B.
If I have a question.
Please.
For clarification, are you using the term population here to mean fishing effort?
Yes, thank you. Statistical population, the thing you want to estimate a parameter for. So I'm not talking about the animal population here. Thank you for that clarification, Tessa. By ensuring representativeness of the sample, you can improve the precision of your estimate, especially if you are able to sample more heavily in areas where your variance of the thing you want to estimate is higher. Another thing about stratified sampling is it allows for estimating something for a subpopulation. Again, I'm referring to a statistical population. So there may be really good reasons that you don't just want one big bycatch estimate for like the whole fishery. You might want specific estimates for different parts of the year, different areas, different gear types, and so on. And so by having identified those different strata, you can get those subpopulation estimates. And ultimately can also just be more logistically easy to carry out. Because then you can kind of focus your efforts like, okay, a team of observers, you guys are gonna work in area A and you're gonna work in area B. And even though we can't put as much effort into A as B for money reasons or access reasons or whatever, we don't need to put as much effort in each of those as long as we're like quantifying those strata separately and taking into account the variances separately. So lots of good reasons to stratify your study. And we're gonna go back into our code. And now we are at example 3B, which starts on line 177. So we're gonna repeat, we're gonna use the same data set that we collected, or sorry, we're going to repeat the same exercise. So don't change anything up in those upper parameters to play with. Same number of sets per strata, 2 strata, same bycatch rates that we were using, same observer coverage that we were using. But now we are going to separately estimate bycatch for the 2 strata and add those estimates together, rather than treat it all as one big sampling scheme. So we're just going to select this block of code from line 182 to line 205. That's going to do that process for us. You can, on your own time, if you want, work through these things line by line to see how the code's working, how the steps are working. It's pretty well annotated, so I think you could follow, most of you could follow through it. But we're going to run that code down to line 205, and we're going to see what our distribution of estimates looks like now. And hopefully your distribution of estimates has better properties now with respect to the true value.
People's histograms look more like this now. All right, lots of nodding.
Okay, and I'm gonna and we're gonna ask, and we're gonna think through a few questions. So what is, the first one is, and you know, let's just get 1 or 2 people to answer that. What's an important assumption? And I've already kind of given the answer in a previous slide, so this hopefully is an easy one. But what's an important assumption about how sampling is conducted within each of those strata?
Hearing that it's representative.
Okay, indeed. Pretty simple, but important. Okay. Can you guys, I'm not going to run through every one of these little questions, but can you guys think of other ways that the fishery observer data, or the fishery itself for that matter, might be stratified? Think about systems you work in or that you want to work in that are on your mind, and think of things that might be important to define strata based on. And then you can just start barking out some answers. I've already given a few, but maybe you can think of some specific ones based on fisheries that you know.
Type of gear I'm hearing. Ooh, crew experience.
Cooperative schemes, different companies,
seasons, areas, different companies.
Fishing closures.
Area closures, fishing closures.
Mm-hmm.
Migratory species.
Migratory species.
Okay, so what do we mean by that?
Just the times, so I guess temporal
Overlap.
Overlap, yeah.
Okay, so stratify by like month or season or something like that. Mm-hmm. So what might happen if what's that?
Regular season. Because if you can't predict the stratum a priori, you're in trouble. So if the season that the animals join your population changes over time, good luck with that.
Yeah. So let's make a distinction between stratifying according to characteristics of the fishery and stratifying according to characteristics of the species that you're interested in, right? So you can do both if you know both. Often you won't, right? But you could imagine like you might want to estimate your BPUE separately for an area where fishing's occurring and you already know that that's like a rich habitat for the cetacean of concern. And then you might estimate separately for a different area where you think the species occurs at lower densities. You often might not know that about the species, right? But you do know that the fishery is occurring in 4 different places that have different attributes to them that may or may not correlate strongly to what's going on with the animal. So there's this latent process, right? This unknown, unobserved process of what the BPUE is in the different strata, right? And if you knew that BPUE didn't vary in time or space, for example, then you could muck up your study and you'd be fine. But if BPUE does vary in time or space, and you don't necessarily have to know where and how it's varying, but if it does vary in time or space, then that's when you need to make sure that you're separately quantifying these things for different strata if those strata are sampled at not the same proportions. Does that make sense? Heads nodding or thumbs up?
Heads nodding, heads nodding.
The question was, there's a whole bunch of ways to stratify.
Yeah, I was just agreeing that it's complicated beyond just incision 2 or to not stratify to what level.
I just can't tell. Yeah.
Oh, good.
Everyone's agreeing with you, Jeff.
Yep.
You can go ahead. You can go ahead, Jeff. Keep going.
So I'm sorry, I just don't hear the comments. What?
Okay, we're going ahead.
I can go ahead. Okay. Yes, there are different ways to stratify, and it's not okay. Okay. So you see my slides now, right?
Yes.
Slides, yes, you see my slides?
Let me see your slides. Why can't you hear me? I'm the closest one to the.
The owl is not living up to this. It's not.
We
Can I just
can
get a
see your
thumbs up if you see
slides,
my
Jeff.
slides?
We can
Thank you.
see them, yes.
Okay. Okay, so we're going to talk a little bit about model-based approaches. Okay, so
Oh, no. I think it's.
I got you now, Tara, or Tessa, sorry, I got you now. Okay. So model-based approaches. So model-based approaches, when we talk about model-based approaches, we're talking about the type of inference that we're making. And we contrast model-based inference with design-based inference. And in model-based inference, we're not assuming a model ahead of time and trying to conform our survey design scheme to that model. It's like we have the data first, and then we are identifying a model often that is drawing upon a relationship between covariates and the parameter that we're trying to estimate. Benefits of model-based approaches. Just some bullets I have listed up here, right? So inference about response covariate relationship from a large sample from your study area can be used to estimate parameters for smaller areas, right? So maybe we didn't, maybe we have a strong interest in knowing the likelihood of bycatch occurring in a particular place and time, but we didn't actually sample there. But we do know certain things about the fishery there, and we've identified relationships between bycatch and fishery characteristics from the sample that we did have. And so now, based on those relationships, we can make predictions about bycatch in places that we didn't estimate. Model-based approaches also can help researchers cope with small samples or small within stratum samples, undersampled areas, and if done properly, we can improve the precision of our estimates. But again, I can't emphasize enough that taking model-based approach is not really a good substitute for still implementing a good representative sampling scheme throughout your study area. If you don't have, okay.
We have a.
If you don't have a good sampling design, you can still get bad inference. You know, model-based approaches can't always fix that problem of undersampling certain areas, oversampling certain areas. There's another challenge is that, question, go ahead.
Yeah, on your previous slide, Jeff, can you hear me?
Oh, she's so loud. See,
I don't know if you can hear.
Maybe walk.
Okay.
Okay, can you hear me, Jeff? On the previous slide, you were talking.
I can hear people, I just can't always see you clearly. On my previous slide, go ahead.
Yeah, there. Okay, so you're that one that you say, okay, try to see if you can
Not
come.
well.
Okay, on you were suggesting one way would be to do inference on a relationship and then extrapolate basically for the whole area. I'm just curious if you know of any real you know, management example where that was applied and used for that situation where you come up with one relationship and then you run with that for the area that you did not sample.
You get the question, Jeff?
yes, yes, there's just a lag. Just be patient.
Okay, I heard that. I'm gonna type something. Okay, yes. So first of all, let me comment on your use of the term extrapolate. So extrapolate refers to making predictions to, you know, a part of the population that's kind of outside the bounds of where you sampled. And it's generally considered unwise to do that. So when I refer to making predictions to unsampled areas, I'm usually going to be talking more about interpolation, where what you're trying to make predictions on, like the characteristics of the fishery that you're trying to make predictions for, have been included in your samples, in some parts of your sample. So you're interpolating into space that's inside the area that you have samples, or you're interpolating into, you know, you've sampled in March and May, and you're trying to interpolate into the month in between April. Okay, so just careful about what you're making predictions on. Are there examples of that? There are a number of examples, some that are cited in our paper, and I'm actually going to list some citations in a slide or two, where these approaches are used to estimate bycatch for the unsampled portion of the fishery, and then what's reported is an overall bycatch estimate for the fishery, not necessarily bycatch estimates being reported in particular areas in space. And I'll show some citations in a moment. But yeah, there are examples as well. I think Simon Goldsworthy with sea lions in Australia has done some spatially explicit bycatch prediction maps, for example. Okay, so just to get back to the slide, so with model-based approaches, Limitations and cautions. Again, inference is not immune to poor sampling design. You need to use covariates that are known for the fishing effort of the unsampled portion of the fleet, right? So if you have, so let's say you have your observer data, and your analysis of those data reveal that there is a relationship between BPUE and the depth at which nets are set. But then for the rest of the fishery that you didn't observe, you have no idea what the set depths are. So now you're kind of out of luck. You can't predict bycatch in those sets because you don't know the covariate value that you've estimated for the relationship you've estimated. So that becomes really important then to somehow either get that information for the unobserved part of the fleet. So like, you know, if fishers are recording logbook data, there are certain covariates that you're asking to be collected, or that maybe you know are already collected, or you know that your sample is representative of the strata, then you can kind of assume that everybody in a certain strata are doing the same thing. So, but anyway, that's just important consideration. If you're going to look for relationships between covariates and BPUE and use those to predict elsewhere, it's got to be using covariates that are available for the elsewhere. Okay, I said there was a slide where I had a bunch of references, so I'm not going to spend time on this slide. This is just FYI. These are all papers that are either in the Moore et al. Article, or some of these are other articles in our special topic. So these are things that you can explore on your own to get a flavor for the wide range of model-based approaches that have been taken to identify covariate BPUE relationships, or to deal with non-representative sampling problems. Okay, back into R we go.
Back into R.
Okay, you guys see R?
Yes.
Yep.
Okay. So you are going to want to load the R data file. Andre, you good? Tessa, you good?
Yeah.
Okay. You're going to want to load the R data file that you downloaded. So that should be somewhere in your working directory. This line of code shows where it is on my machine. You are going to need to specify where it is on your machine.
If you're running R,
and then just run that line of code.
If you're running R from the folder in
and Andre, give me a thumbs up when it seems like people have done that.
So what I do is I run R from the same folder that all our data is, and I get rid of that whole spiel about C:\Jeff and just have this piece here in quotes, and you're working in you're running from your current directory, it'll find it immediately. So you don't need to put it in the whole string if you don't want to. Has anybody started to try to load that file? I saw one thumbs up. Anyone having problems getting that data file loaded? It's called whatever.
It's called coursedata.rdata.
Yeah.
Right, but what's the years?
It should. Yeah. It's you mean the object is
No object.
Yeah. Okay, we got one more good. How are we doing on this side? Got it? You got some data? Yes, we have some data. Yes. Just get it. Just basically, you needed the course database. Yep, and just get rid of everything from the slash thing. Yep, so get rid of that. And all the way back to the quote. Return, and it says going down. You're in the right folder. Shouldn't be an R2. Not the data file. When you got the data file, where's the parent? Go to file. And you say save as.
Anybody else need help loading the data?
Okay, you're in whatever that is. Yes, you copy that and then put it in Fran's file, folder. So you have to go to code, place C colon J. Okay.
Well, no.
Just get rid of everything. Yep. You may need to change a few slashes. Get rid of the bits further on. And change the front slashes to back slashes. No, other way around. It will need to be. Okay, we just, anybody else struggling? Everyone else got their data?
Yeah, sometimes.
I think we're just waiting on one last person, but you might want to get going. Is that you? No. Working? Go back. Always hit the run.
We good?
Oh, it doesn't like.
We're waiting on one more person, Jeff. We're very close.
Could you find that file, move it to a directory? So this is some sort of download folder. But if you can move, you find them, you can go down the time. That's me. It should be a C. It should be a course. Gosh. It's called course day. It should have been in the, and if you need it, I've got it as a. But we're having a slight struggle, but go for it, Jeff.
Okay, I feel like I need to start moving forward a little bit. So hopefully everyone will get there in a moment, or you can huddle a little bit if needed. Okay, so for those of you who are there, you can take a look at the structure of the data, and there's two lines here, line 222 and 223, and if you execute those, this just kind of shows you the attributes of the data. So you can see if we look at the obs.data, this is your observer data set. So I've pre-constructed for you a data set, one that is for the entire fishery. So we have, you can see looking at the S data that there are 5,000 rows in this data set. So let's think of those as our fishing effort units, 5,000 sets. that occur in XY space. And we know from logbook data, for example, that we know the sets, the depth of like the bathymetric depth in which those sets occurred. We know the length of the nets. We know how long they soaked in hours before they were hauled back in. We know, let's say from like satellite data, a productivity index of the environment, like a chlorophyll measure or other. And we know if that set was observed or not. And this, of course, is not known to the researcher, but to me creating the data, I know whether bycatch occurred in that set or not. And then we have the observer data, where we sampled a fraction of those sets. We sampled 698 of them. We had observers on board for 698 of the sets, and we have those same covariate values. So we know where the set was, XY space, the bathymetric depth, net length, soak time, productivity index. And for these sets, of course, we do know whether there was bycatch in those, because that's what our data are. We're going to take a look at these data. So lines 226 to 228, we're going to visualize the fishery. We can execute those lines. So here we have our map of 5,000 sets that occurred in the fishery. Again, hopefully yours is not so compressed as mine. And I know a bunch of things about this fishery that you don't, because I created the data. And the first thing I'm going to ask you to do, and this is sort of rhetorical, but look at the plot, and does it appear visually that the observed sets are a random sample of the whole fishery or not? Or that, or are there areas that are oversampled and undersampled? Similarly, does it look like bycatch, the spatial distribution of bycatch events is random, spatially random throughout the fishery? Or does it look like bycatch is occurring more heavily in certain areas of the map? Okay.
Yes.
So now we're going to go through an estimation exercise using a design-based approach. Okay, so we're not going to do the model-based. We're not going to apply the model. Yes, please. Go ahead.
No, there's no question. Andre was just getting a feel for the room. You can go ahead, Jeff.
Got it. Very good. Okay. So now we're going to estimate bycatch using a design-based approach where we assume that the fishery has been randomly sampled. Okay. So we think that we've done a good job of randomly selecting sets in the system. Or at least we think we've done a good job of that with respect to how bycatch rates vary in the system. So we're gonna estimate bycatch from these data using the methods that we've already done. A simple estimator where we quantify how much bycatch is in our observer data set. We divide that by the number of sets that we observed to get our BPUE. And we multiply that by the total number of sets in the fishery to come up with our total bycatch estimate. So that's lines 235 to 237 in the code. Go ahead and run those. And you'll have your bycatch estimate that you came up with. And you can compare that to the true value by executing line 240. And my guess is that some of your estimates are pretty close to the true value. Some of them are a little off. Some of them are maybe way off. If we, again, replicate our experiment 1,000 times by executing the block of code from 243 to 250, we can see what our distribution of estimates looks like. So go ahead and do that. And then I'll take a verbal thumbs up from our hosts after people have done that and verified that your histogram looks sort of similar to mine.
All agree.
Yep, all good here.
Don't do this.
Okay, so we see that our approach has been biased clearly because our distribution is not centered on the true value. So we've and I guess I would ask for someone to respond to whether this surprises you based on what the data just kind of looked like in the map.
No.
No surprises here.
So there's our map with data. No surprises here. Okay, so we see that we've oversampled in areas where BPUE was lower, and we've sampled less in areas where BPUE is higher, right? So we have an unrepresentative sample, so we haven't done a good job of representatively sampling the fishery. But let's see if a covariate to BPUE model can help us out. So if we go down to, so what we're going to do here is we're going to use a GLM based approach. And my hope is that a fair number of people in the room are familiar with generalized linear modeling. If not, that's okay. There's a lot of code in here to help you out. GLMs are, you can think of them as a regression framework that is more general and flexible to cope with non-Gaussian response data. So the code that the way I'm going to help you out here is that I've provided the lines of code needed to run a GLM where we have included all the covariates in the data set. So if you look at line 257, so we don't know which of these covariates is related to Bycatch, but we're just going to assume in this first model that they all are. So we have a GLM expression that says Bycatch is a function of space, where we are in the XY space, the bathymetric depth of the sets, the length of the nets, the soak time, and productivity. And we're gonna run that full model. So you can select these first two lines of the code, lines 257 and 258, which runs that model and shows us the statistical output. So go ahead and do that. And what we have then are estimates for the slope coefficients for the linear component of this model. And we have standard errors associated with those coefficients. And we have p-value estimates that would suggest that soak time mattered. Maybe nothing else really did. But for those of you familiar with model selection approaches, you'll know that when you have a bunch of variables in your model that aren't important, it can mess up. Yes, go ahead.
I was just going to say, you might want to comment on an implicit assumption here, which is everything.
Okay, I'll continue. That if you have a bunch of junk variables in your model, it can mess up the estimates for the variables that are actually important. Okay, thank you, Andre. Yeah, yes, this model here says that all of these variables are linearly related to the response variable in the linear part of the model, in the link function space. Of course, we could explore other shapes of relationships. We could explore quadratic relationships and others. A lot of people will use generalized additive models, GAMs, to explore more flexibly shaped relationships between covariate and response. I'm purposefully staying in a pretty simple framework here, a GLM, and we'll keep things simple for now and assume that if there is a relationship between bycatch and these variables, that relationship is linear. But that may not be the case in reality when you're doing your own real modeling. Okay. Okay, I will move on. If we look at, so now that we have our model, we need a way to predict bycatch for the rest of the fishery that we didn't observe. So we're going to extract our coefficients by executing line 259. So here we have an object, a GLM object that just has our coefficients. And hang on a sec. Okay. And we are going to use those coefficients to predict the bycatch in what's referred to as logit space here, because we're working with binomial process. And if this is not a familiar concept to you, don't worry about it right now. There's a linear part of this model that we're predicting, and then we'll do a transformation to go from that linear part to estimates in the space of the real data. So we have this line 261 logits, and we're going to execute that. So what this has done now is for every row of data in our complete set of data for the fleet, the fishing effort data, we now have a prediction for the linear part of what bycatch is for each of those. And if we run the next line of code, line 262, that transforms the linear part of our model, the logit, into an actual bycatch estimate for each set. So we can run line 262. And now we have an estimate of bycatch for every set in the fishery based on the covariate values for those sets and the slope coefficients for our model. And now we can add those individual set catches up all together, run line 263, and we have an estimate of bycatch for the whole fishery, which we can again compare to the true value. So you're comparing line 266. Sorry, you run line 266, that's your true value, and you compare that to your more recent model-based estimate.
I have a question, if you can hear me.
And for many of you, that will probably be closer to the true value. Your new estimate will probably be closer to the true value than your original estimate. That might not be true for all of you, and that's okay.
Jeff, any reason you?
I'm going to pause for a moment to see if there are questions and just to make sure people are caught up.
Firstly, is everyone caught up? Question for you, Jeff. You've predicted for all of the sets, including the ones you actually measured. When I've done this, I would only predict for the cells that were unobserved. So such that if you had 100% observer coverage, the model wouldn't do anything. Any reason why you predicted for all, all sets?
Yeah, that's, simpler code.
Works for me.
But yes, I would tend to follow what you just said. Yeah. Okay.
We all there? Everyone, it's all running so far? Cool.
Okay.
Nothing else? You've run a glimpse, so that's going to be a good thing in your life.
Okay. Now, one thing you'll have needed to do, like you'll need to do now if you haven't already, is type or run this first line of code at the top, library mass. Hopefully that's just straightforward for everybody, because I think that's a package that's pre-installed for everybody in R, and you just need to load it. Hopefully I'm not wrong about that. So a quick thumbs up that we're all good to move forward. Yeah, okay. Okay, so we're going to now repeat, again, we're going to go through an experiment now where we do many replications of the process to obtain a variance estimate, okay? Because when we, because those coefficient estimates, again, this might be foreign if you're not, like, if you don't do a lot of regression or GLMs, but those regression estimates are correlated. So if we want to resample from the distribution of the individual coefficients, we can't just randomly independently sample from each coefficient. Those coefficients are correlated so that if one is a little higher, the other one is expected to be a little lower, based on how we're fitting the data. So what we're going to do right now is sample from using a variance covariance matrix. That's why we had to load the mass package just now. We're gonna, again, not important for you to understand some of these details. This is just a process we have to go through to get some variance estimates. So we're going to execute this line line 270 to extract our variance covariance matrix from the GLM object. And then we're going to use multivariate random distribution to sample from all of the coefficient distributions. So you can execute line 271. Okay, so now we have, for 1,000 replicate experiments, random draws of our coefficients. And then we're going to use those to come up with bootstrap estimates of variance on our bycatch estimate. So you can just highlight lines 272 to 278, run that, and you'll have a distribution that is essentially an uncertainty distribution for the bycatch estimate from the GLM model that you've run so far. Thumbs up when you've gotten to this histogram.
Yep, looking good.
Yep.
Okay, so if we compare that to our previous histogram, and you can use these, if you're using RStudio, you can toggle between your current plot and your previous plot. And does it look like, by using a model-based approach, even though we haven't really tried to find the best model yet, have we improved our estimate in terms of reducing bias? Maybe just head nods and What do we think?
Better in.
You're getting a 4.5 out of 10 here, from what I can see.
In terms of people getting to this point, or in terms of people thinking that we've done better?
The latter.
Okay.
We've done better.
Yeah.
Okay. So we've done, I would say we've done better, but we're not there yet, right? So we've reduced bias by taking a model-based approach, but we haven't eliminated bias. And part of that might have to do with the choice of model that we've used at this point, where we've included all covariates and made predictions from all covariates, even though some of those covariates were clearly not important. Now, I'm mindful of time. We have, my clock says 4 or 5 minutes left, right? Okay, so the last exercise that I had, I was hoping to have more time for you guys to do this next bit on your own, which is to actually see if you can find the better model, find the best model, find the covariates that are actually important using a model selection approach. And I was gonna give you guys like 20 minutes to just do this on your own. We don't have time for that, unfortunately. So I'm gonna walk you through this last bit, okay? So let's see if we can improve on the model that we've used so far. So I have a little bit of cheat code here, and you don't have this code, so you guys are just gonna have to follow along with me. Okay, does that work for you?
Yeah.
Okay, so there's this handy little function in R called step, which is basically a way of, based on AIC, to identify a most parsimonious model. So I'm going to run that line of code, and this output that I'm scrolling through shows a whole bunch of progressions of R trying a bunch of different models and getting AIC values for those. And as it's going through this kind of like stepwise process of trying different models, ultimately it gets down to the bottom and it says the model that it likes is depth and soak time. So since the model selection process has told us that that appears to be the two useful variables, I'm going to basically rerun the GLM process just using Bycatch as a linear function on the logit scale of depth and soak time. So we run that, we get our output. We see that both of those terms appear to be quote unquote highly significant. I'm going to extract the slope coefficients from that GLM object. So here's our intercept, here's our slope term for depth, here's our slope term for soak time. I'm going to, based on those slope terms and the actual values of depth and soak time in all of the sets in the fishery, calculate the logits for all of those, from which I calculate the catches, and then add those up across all sets to get total bycatch. And again, as André points out, it would probably be smarter if I just did the estimation for the unobserved sets. Okay. But now I have an estimate of 427, which I'll compare to the true value of 440. Not bad. I'm going to go through the bootstrap process to construct my variance, my confidence distribution, essentially. And we'll take a look at the histogram. And shockingly, it looks good. It's beautiful when you can. It's beautiful when you're in control of your own experiments. But I think, I hope what this illustrates is how using, here I had a fishery that was not sampled representatively, and we saw the bias associated with the estimate and we tried to apply a simple design-based estimator that ignored that non-representativeness. But by applying a model where we explore the relationship between the covariates and the response, we were able to reduce the bias in one go of the model, and then, in this perfect world where everything's controlled in a computer, ultimately eliminate the bias when we not only were using a model, but we had the right model. So that brings me to the end. I'm sorry you guys didn't get to kind of like try that last one on your own. I hope that these exercises have been useful for just exploring fundamental concepts, important concepts of like study design and some kind of key statistical concepts to keep in mind when you're going about estimating bycatch from observer data. So I'm going to stop there.
Okay. Well, firstly, this has all been about making good decisions and learning new things. Well, my decision was, I was actually in Australia on Thursday, and I could have done this remotely. And I am clear that I should have flown here and been here, because if you thought the delay on the last call to San Diego was going to be bad, you can only imagine what it'd be like to Hobart. So that's the first thing. Second thing is I'm actually giving work done by Margaret or Megzi Cycle. She would be far more awesome than I would be at giving this presentation, but she is on a ship in the middle of the Bering Sea, I think. And if you thought it was bad to be in San Diego or Australia, you should just try the Bering Sea. So she's not here. I do want to mention one thing before I get into the talk, and that is one of our team members, Gisli Vickingson, passed away about 2 weeks ago. Some of you may be aware of that. Gisli was a colleague of mine for the better part of 30 years, and a true gentleman, and a scientist with an enormous amount of knowledge of both how cetaceans are managed. He was the head of the Icelandic delegation to the IWC for as long as I can remember, and one of those few people who could balance the politics and the science of working in the cetacean area. And I just wanted to reflect on that. He was a great guy. It was a real shock when I heard that he'd passed away. Okay, so move on. Okay, so I'm going to be talking about another of our products. This is a ShinyApp that we produced, or Megzi produced. And the idea here was not to produce a really sophisticated stock assessment package. There's a couple of the papers we produced that get into some real pretty heavy math and modeling. This is a fairly straightforward tool to really illustrate and teach and get an understanding of the implications of bycatch. Where we are at this point, we've talked a little bit about collecting data, both abundance data and bycatch data. We're going to do a little bit on some models. I'm not going to get into any math, but the idea at this stage is now we're bringing together the information we've got and how we can make inference in terms of sustainability and achievement of goals. I'm talking about the tool now, and I'm going to be talking about management later this afternoon. In some sense, perhaps I should have done it the other way around, but hey, life is the way it is. I mean, I was thinking at this point, you've learned all about abundance estimation. Everyone wants to see Megzi, and so that would have made more sense to do it. But we're going to keep going. So we've got data. Ooh, that's exciting. Okay, well, that was not quite what. So you're going to have to use your imagination. PBR is going to be central to this presentation. There is an equation. This is actually going to be the equation I've got. PBR is the product of three numbers. The first one is a minimum, quote unquote, estimate. It's really an estimate that's close to a minimum estimate. In this case, What we were talking about abundance estimation. Abundance estimation gives you an estimate and it gives you a measure of precision using a CV. And so N-min in this case is the lower 25th percentile of the abundance estimate. So if this is the probability distribution for abundance estimate, your sort of best estimate would be here, and we take a lower confidence interval. So this is a measure of precaution. So the lower the percentile, the more precautionary you're going to be. The more certain you are that the true abundance is greater than your N-min. The next is 0.5. The good news, I'm going to spend a lot of time explaining what 0.5 is. R max is the maximum, let's see if it actually does it, is an estimate of the maximum rate of increase for a population. And the final thing, if you could see it, would be F subscript R, which is referred to as the recovery factor. Although those of us who are in the profession would call it the fiddle factor. Kristy disagrees violently, but that's good because that's exactly the response I wanted.
Or fudge.
Oh, sorry, it's the
No, that's
fudge.
worse.
It's the fudge factor, you're right. So the good news is the fudge factor or the fiddle factor has a set of guidelines, and they are policy oriented. So it's perfectly reasonable for them to be fiddle factors. So essentially, if you have a stock that is at OSP, which is not the Office of Sponsored Programs, which is what it is for us, it's optimum sustainable population. You can think of that as, and we'll touch more about that in the next talk, is the population size at which the number being added to the population is maximized. So for those who have a little bit of population dynamics, the maximum rate of increase of a population occurs when? At the lowest possible population size, the rate of increase. OSP is the point at which the number being added to the population is maximized. For those who've done a fisheries class, and again, Kristy, close your eyes because I know you're not supposed to, yeah, it's not eyes. It's essentially maximum sustainable yield, but we never talk about maximum sustainable yield in the sense of bycatch because we're not trying to maximize anything except population size. So FR can be up to 1 for stocks that are essentially doing fine. 0.4 to 0.5 for species that are threatened or endangered, and then threatened or depleted, and then very low for stocks that are threatened, basically. So this is a way to enhance the rebuilding rate through the PBR. So the idea of this tool, and everyone should have a really, really short R script, like has 3 lines. One of which is to install a package, a second is a library, and the third is the call to the tool. So how many people did install the package? I realize some of you work for governments that don't allow you to install packages, but if you don't, I've got the URL coming up in a moment. But for those of you who've got the package, run the package, and you can at least watch the package doing its thing while I talk. So is everyone getting the package running? Hopefully all is well.
What is
I
the
don't have
package?
a package.
Sorry?
Can we just,
Well,
it was in the instructions in the email,
Yeah.
but maybe you can we put it up on Zoom?
I'll go get it.
Yeah, just pop it in the chat. You have to have, that's right. To install it, you have to have dev tools because it's a package. Okay, so the package comes in, as a sort of implied, comes in 2 forms. The first one is online Shiny tool, hosted somewhere in a big computer somewhere. It probably suffers from the same problems that we had this morning with Jeff's tool, which is once you get too many people running it, it splits the dummy. So what you're actually using is you're using the R package. For those of you who are interested in learning more about population dynamics, all the functions that we use in this package are available for people to play with. So you can learn a little bit about PopDime if you're interested. The GitHub site that Megzi works on is available as well. So you can you can really get into the code and play around with it. There's a paper published in JOS, which is the Journal of Open Source Software. Has anyone ever published there? The weirdest peer review process you've ever had. Someone actually checks your code and comments on your code rather than on the text of the paper. So it was a cultural experience to have my code examined, but it was fun. So it's published there and it's open access. So what we're going to do now, I'm going to go through a couple of screens and then we're going to actually get into the ShinyApp itself. So there's a number of bits, and the cool thing is this is a great audience to try this out. And we've never had an audience where we've had multiple languages. So the default is English. How many French speakers do we have? Voila, you're French. Any Spanish speakers? Voila, we have some Spanish speakers. We have someone who speaks like 16 languages. Our aim ultimately would be to have more languages, but that's my lab happens to have a French postdoc and a Spanish postdoc, and guess what? I've got Spanish and French. So the cool thing is, while we do this, I want you guys to be in your natural languages to see if it actually works. Because I am an English speaker, which means I only can speak one language. Yeah, that's the nature of being English. Sorry? Okay. So the tabs we're going to go through, one is just a simple tab that's designed to actually help managers understand how PBR is calculated. So it does nothing more than multiply three numbers together, but sometimes that's what people want. So we'll play around with that. The rest of the calculation, the rest of the package is based on population dynamics model. It's a pretty simple model. You can think of it as an age-structured model where we model a population with a calf survival rate and an adult, non-calf survival rate. So we just distinguish two survival rates, even though in reality we'd want more particularly. And we've got a reproductive cycle. So this is very simple age-structured population dynamics model that we're running. And we've obviously got Bycatch. And I don't quite know how it's catching any bycatch, but anyway, there it goes. So this tool is not meant to replace sophisticated stock assessments. Really, it's to help managers and scientists essentially trying to integrate what conclusions can you draw with the information that you've got about abundance and bycatch. It can also help you just to understand, in a very rough sense, how, sorry, is there a question? Oh, by the way, if you want to interrupt me, I've got a very loud voice, so you probably can't, but you can give it a go. It also allows you just to basically get a sense of how cetacean populations interact with bycatch. As Maxie points here, it's not the tool that you use for everything, but hopefully it will be a tool that you'll use for some useful things. We actually wrote a paper that sort of complements the tool. This was published in, where was it published in? Journal of Applied Ecology. So everything you've heard today has really been focused on PBR-based management. This was a paper that we wrote where we used methods we use in fisheries for data poor species, because a lot of our cetaceans and marine mammals generally look rather like data poor fisheries. Very few abundance estimates, poorly estimated catches. That's actually a very common situation in fisheries. So we wrote this paper to give a different perspective on how can you manage it if we don't have the kind of data that we expect for PBR, but I'm not going to talk about that. So there is the URL. So if anybody, Paula, I think you're the only one who didn't have the package.
I got it.
You got it. Okay. So does everyone have either the tool running? Have the French folks click the French button?
Yeah.
Have the Spanish folks click the Spanish button? Click the Spanish button. I really like the idea of giving a truth-free language tutorial. I just think this is cool. Okay, and Paula, is the URL working for you?
I'm getting there.
Okay, I won't move until it disappears, otherwise.
So the Spanish person
So if you want to see at the top, there's English, French, and Spanish. You just click select the bullet, and it'll change the language in the document.
So sorry, what are the instructions for the people on Zoom?
Oh, if they're on Zoom, run the R script that I gave.
Dev tools install, but then once it's installed, then what?
Oh, there's a little script that we handed out.
I didn't get that either. It's just library and then the MMBIET points and then run_app.
That is.
Yeah, we didn't have that.
Oh, we didn't send it out.
And well, I didn't have it ref points.
I have
Okay.
to go online, to find that.
Oh, really?
Run
Okay.
app,
Well, there you go.
ref points. Okay.
If people are online and they can just use this URL and go straight to ShinyApp.
So sorry, once they install, after installing,
Then you once you've installed it, you say library whatever it is, ref points.
Yeah.
And then run underscore app
And then parentheses.
and parentheses, because
Can
otherwise.
you show the direct link again? The direct website?
Sure. There we go.
I have to type all this into that.
Sorry.
I just have to type all this into
Oh,
the
sorry.
chat.
So if you go there, it says on the top that it's a beta version. For best results, please use the best version.
My lawyers have told me I'm unable to answer that question.
But you can answer it in French.
I think what that's meant to mean is that the GitHub is obviously more updated than the Shiny. It's just when last we sent it up to Shiny. Are you good, Tessa?
Well, I haven't had anything from anybody online, but when I use these instructions myself, it doesn't actually run the app.
Which instructions?
This one, so install.
Yep.
Library, run app.
Okay, give me 2 seconds. I will copy. Oh wait, wrong computer.
If you project your R, maybe it'll show you.
I can put.
Share your R and just take those things.
There it is. Let's pop it in. Put it in the chat. Bigger. So they. Oh, so if anyone wants to run this from our tools, this is the instructions. Is that a question?
No, just a comment. I run it in Spanish. It seems fine.
It's working?
Yeah.
Cool.
Yay.
We like to hear that. And the
Good
French
feedback.
version?
Yes, but there is a problem with one tab.
Oh,
But actually, it's the same.
Same in English.
Oh, one of the tabs. Okay.
The calcul is not, the computation doesn't work.
huh.
Which tab?
So for
Solve
Bycatch.
for Bycatch.
Okay.
If you have to specify the previous tab to get that one.
You gotta build towards it.
Yeah,
It's the beta version.
it's the beta version. Yeah, well, the project's over. It's not gonna. Please deposit more money. For a small amount of money, you can go to the alpha version. Okay, does everyone have the tab, have one of the products going? Paula, are you good? Okay. Okay, so my solution to the whole this never works is I've got two computers running the two presentations. So I just got to remember to change screens back and forth.
You said to do the simple tab.
Okay, so what we're going to do is I'm going to take you through a couple of examples. I'll just keep the time because we also got a break. So the first tab is going to just do some really simple projections. And this may come as a huge surprise to you, but the tab that we're going to use is called Simple. Hey, there you go. Why am I talking? You guys know exactly how this works. This is an example that we set up for bulbous seals. We know actually quite a lot about these guys. This is the Bristol Bay population that motivated this. The kinds of things that we need to run the app are going to be, what is the population size? Roughly where is it in terms of how depleted this population is? So according to whoever set this up, it's somewhere around, we're going to score 75% carrying capacity. And then we're looking at different levels of bycatch that could cause this population to decline. So what we're going to do, let's go to the app. And I'm going to run this, it says optimistically. Okay, is it gone? Oh, interesting. It's not showing, so I've got to share another screen.
You probably just have to do Alt-Tab, you know, because it doesn't run in hard, it just creates a window.
Yeah, no, that works. You can see this? Okay. So let's go to the simple tab. Okay, so if you are running this in R, you'll see it's actually spitting stuff to the R console as well. Don't worry about that. That's just warnings and stuff. So what we want to do, I've lost my notes. We want to have a fosid seal. So we're going to go firstly to Marine Mammal Life History and select the seal. Everybody see where I am at? So this tab here, we're going to say this. Remember, the stock was at 75%. So which of the three options do we choose? Decline by 25% sound about right?
Yes.
Okay. Then population size, what was it? 32,000. Okay, now what we want to do is to say what are the two other things we can specify. One is what is the range of bycatches we want to look at?
It's 32,000.
Sorry?
32,000.
Okay. So now we can choose, at the moment, the range is 50 to, let's bump that up to, let's go up to, not very good with, I get that to 2,500, 1,000 to 2,500. Okay, so what it's doing here is it's projecting forward under those levels of bycatch. There's three levels it's choosing, nearly close to 1,000 to 2,500. 1,000 is essentially says it should continue to rebuild. The middle is fine, and the high one is pretty bad. You notice there's a big width of the projections. That is the uncertainty in the bycatch. So basically, when I say it's 1,000, it's 1,000 in this case with a CV of 0.5, and we can change that. So I'm now saying, what happens if it's the same average level but less variability, right? So this is a tool that allows us to change the population size, the level of bycatch, and the variability in that bycatch, and to see what the trajectory is. So what time is it, by the way?
2:56. Yeah.
Okay, so we have just enough time for me not to make any progress on the next. Okay, so we covered that. It turns out the true PBR for this population is just over 1,000, which is good because when we get 1,000, things look pretty good, right? So that's a good thing. It turns out the current bycatch is way below PBR, so everyone's fine. The next thing I want to talk about is what's called the advanced option. So that's the second option. And what we're going to do is we're going to essentially use the same example that we had before, so the seals, and we're going to add in a couple of bits of uncertainty that we've talked about. So we're going to essentially specify the level of uncertainty in our abundance estimate, because the first run I did, I assumed that it was 32,350. I'm pretty certain there's a lot more uncertainty than the 350 would indicate. So we're going to give it a CV of 0.2. We're going to choose a range for bycatch between 0 and 500. I'm working in absolute bycatches, although I could use a bycatch rate. So instead of saying an absolute number, 5% of the population could be specified as well. There's a whole bunch of options about how many simulations do you want to do, and do you want to produce fancy plots. We'll have a little look at that. And then the final thing we'll want to specify is this thing called maximum net productivity level, NMPL. So NMPL is, remember I talked about OSP, the optimum sustainable population? Essentially, the optimum sustainable population is the point where you get maximum production and bigger, right? So if you're bigger than that, that's cool. And essentially this variable determines where that optimum sustainable population occurs. So this is saying for this default, it's half of carrying capacity. So to get the stock back to half carrying capacity, you get the big tick according to the US MMBIET. But we can modify that when we're doing some simulation. So what I'm going to do now, I think it's probably coffee time. Is that correct?
Yes.
Yes. So let's take a coffee break. Come back, but when everybody comes back, it'd be great if you got back into the tool and set up the simulations to do an advanced projection with these specifications.
Are we leaving lambda and the survival parameters as whatever they showed up as?
So lambda is R max, or 1 minus R, 1 plus R max. That whatever is in that tab is the default value for R max. In the simple tab, once you select a species, it selects the default R max. In this tab, you can change R max, which they don't do very often for US applications, but it can happen. It's possible, but unusual.
So just to clarify, these values here are the ones that we'll be using?
Yes.
Okay.
So
anything else you just leave as what it talks about.
yeah, I mean, I'm going to give you enough, in the spirit of by the time you leave here, you will know enough to be dangerous. Right?
Are we still doing the faucet?
Yes, we're going to be doing a frozen. So
30 minutes.
30 minutes to have coffee and be ready for an advanced test. So you sound as if you're actually in a class. You volunteered to be here. Well, that's because we've never had temperatures in the 90s before.
Okay, well, I guess we'll get going again. 3:30.
Yes, boss.
Break is over. So André, do some advanced work with us, please.
Okay, we're going to do some. Are we going to do some advanced work? Okay. So I hope everybody, in addition to having a really good cup of coffee, had a chance to look at the advanced tab, which I'm now going to go back to. Don't laugh, just pretend that you listened to me and that you did actually do it. Where's it going? Yep, there we go. Okay, so here is the advanced tab. There's a whole bunch of stuff here. Most of it actually replicates the simple tab, but essentially what the advanced tab does is allows the user to change some of the parameters away from the defaults. So for a posted seal, these are our default parameters, but in some cases, if you may have more information about your particular species or stock, the stock in this case, and you can then change those parameters to match what is appropriate for you. Lambda max is essentially 1 plus R max. So this is the maximum rate of increase. To be honest, the most important parameter in any management system is R max, because R max determines the rate of increase. The rate of increase relates directly to essentially what proportion of the population can you take. So the bigger the value of R max, the bigger the sustainable take, if you want to call it that. So generally, in the US at least, we have some defaults for the R max or lambda max. But if you happen to have data for a particular population. We'll come back to this hopefully at the end, but if I remember correctly, the default lambda max for, let's do a PBR test. What's the default lambda max for a cetacean? Kristy, would you happen to know this? 4%.
Yeah, 4 was sticking in my mind, but I didn't know if I was supposed to say 0.04 or 0.4.
So it's 4%, right? That's the default rate of increase. How many humpback whale stocks do we think are going at a little bit more than 4% per year? Just about everyone we've managed anywhere in the world. So while 4% is a good default for cetaceans generally, for particular stocks or species, that's not going to be the case. And you put in a stock specific value. We're busy doing an assessment of North Pacific humpbacks, and they're doing on average about 7% per year, and they're nowhere near depleted. So the rate of increase when they were really low was probably even higher. So you've got the ability to be flexible in this advanced tab.
For the record, Dennis knew the default for cetaceans.
Gold star, Dennis. He's a bean counter. He loves these things. I'm a bean counter too. So the other things we specify are what's our range of bycatch, how uncertain is the bycatch, where do you get maximum rate of increase. If we specify all that, you hit the big run button.
Sorry, what was S not and S?
Oh, what is S0 is the survival rate of calves.
Oh.
And S, what's the other one? A or O? 1+ is the survival rate of animals 1 and older.
Thank you.
And again, those are defaults based on a meta-analysis. If you go to the, I think it's called the About the Model table, a tab, that'll give you all the biological parameters that we pulled out based on a piece of work that Jeff Moore did. Was that a question?
Well, I was wondering, is the bycatch mortality range to explore still between 1,000 and 2,500?
No, I moved it a little bit for this, but you can do whatever you want. Okay, so did I run it? Where are my pretty? They're my pretty pictures. Okay. So when you run when you do the projections, it'll do a variety of outputs. This is just the trajectory plots that we had before. So this is the population size. Oh, I told it should start at half K. That was a mistake. It should be 25. So I started a bit higher than it should have. And in this case, for the range of catches that I put in, bycatches, it's stable. This is what's called the production function. So when we talk about OSP, which I'm going to talk about in the next lecture, next talk, essentially anything above 0.5 under US policy would be considered to be within the optimum sustainable population level. So US management aims essentially to get stocks to 0.5 K and above and keep them there, which is of course very important. There's a whole bunch of other outputs. I'm not going to go through all of them. We produce a couple of statistics that are quite useful just to summarize how things are going. So what's the probability of rebuilding to OSP or MMPL after 50 years? In this case, essentially 100%. That's because I started at MMPL. And so there's a whole bunch of ways of summarizing things. Those are graphical, tabular. I've also got graphical down here. We've got violin plots, etc., etc. So there's, I'm not going to get into all of these. You can play around with them. The next thing is really straightforward. This is the PBR calculator. So if you can't multiply 3 numbers together, this is going to help you do that. So you can enter your best estimate, your minimum estimate, the Rmax and the FR, and it'll do the calculation and actually save the result as a file on your computer. So you can calculate PBR and essentially it allows you to save the results as things like JPEGs and things that you can then pull that into other products. Let me just get back to the other lecture on the side. There's lots of pictures. Okay, the really cool thing is the what's called the save for bycatch option, which now hopefully works rather than crashes. So what this is going, what we've done so far is to say, if we have a population and we have a certain level of bycatch, what's going to happen? This is answering the inverse question, which is to say, here we have a population, and I'm going to run it for a fur seal, 100,000 animals, CV of 0.3, at 25% of 25% carrying capacity. We're going to look at a bycatch rate. So this is the proportion of the population that's bycaught rather than the actual number. And then we're going to do a CV. So what we're going to do is we're going to first just use the advanced tab to just do some forecasts. And then we're going to ask the inverse question, which is how much bycatch can you allow and still achieve the rebuilding target? Okay, so that's, and you see how I've turned this around. One is what happens if, and the solving tool is asking the question, what is an allowable level of bycatch? So this goes to some of what Kristy was talking about having goals for your management system. So let's see if we can do that. Okay, firstly, do I have someone who isn't gray? Sorry, Simon, you don't count. So I want someone who's young and gray and can remember these numbers, because the moment I close this down, I'm going to forget what's here. So anyone young and has still got a memory?
Or someone just write it down.
Oh, no, that's too simple. That's just giving up.
I got it, go ahead. Move on.
Okay. Okay, so let's go back to the advanced tab. So what do we got? We've got a fur seal, right?
Correct.
Okay, so let's updated the parameters. How many animals do we have?
100,000.
100,000, really? Oh. Okay, what's the CV of abundance?
0.3.
0.3. Why does this all seem so new to me? Okay, which stock is depleted to what?
25% carry.
Okay, we can do that. There we go.
Wait, no, it's reduced by 75.
Oh, it's
25.
at
Oh,
25%
okay.
carry
No,
capacity. I don't know what
no BS for me this evening. Okay.
I don't know
Okay, are we, what's the bycatch is?
how- Zero
Rate.
to 0.0.
Ah, yeah, I got you this time.
Yeah.
Option we need to select is bycatch rate, correct?
Yep.
So let's select that. Oh, look at that, it changes the x-axis. Okay, so what was it? 0 to
0.03.
0.03?
That's what you
That's
said,
it.
and I thought, does he mean that?
Yeah, no, he does, because 0.3 would be
For seals.
fine for an anchovy. Okay, do we want to do anything else? No. Run projection.
What's CV of bycatch?
Oh.
0.2.
CV of bycatch. What did I do? Oh, I completely screwed it up. Okay. Yeah, I needed, I selected 0.3 and then a bycatch CV of 0.02. Does that look better?
Wait, what was the
0.03
bycatch
and
CV?
0.2.
0.2. How does that look? So bycatch rate between 0 and 0.03 and a CV of 0.2 on the bycatch. Okay, hold your breath.
What did we set MMBIET? Just left it at 0.5.
Left it at the default of 0.5. Okay, there we go. It looks pretty good. Everything's decreasing, which is good. We've chosen some we're starting where we should be. We've got a CV, we got that. It all looks good. Okay, but now what we want to do, what do we want to do? Let's go to the next slide. Okay, so we've done that. We've used the tool to project forward, right? So now what we want to do is to say, well, we want to rebuild to MMPL within 30 years with 50% probability. And what we want to do is to find what level of bycatch rate would do that. Okay, so does everyone see what we're trying to do? So we're at 25% of unfished. We want to get to 50. We want to do that in 30 years. And we want to do that with 50% probability. Okay. Now, in principle, if we go back to the other screen here, if we go to the table, we can look at that, and remember, this is running it for 3 different levels of bycatch rate. So this was 0.03, 0.15, and 0. And so this is 10, 20, and 50. So can anyone tell me what 30 years is going to be? You can, you're smarter than I am because it's not on the table, right? So that's great, but doesn't tell us what we need. So let's go to the solve for bycatch. Okay. So I've selected the solve for bycatch option. Okay, so what's our recovery goal? Can anyone remember where are we trying to recover to? 50%, which is what we've got. Okay, when do we want to rebuild to by then?
Now.
You want now? That's really hard. That involves supplementation. We don't. I think that's sorry.
I said I'm with Tessa.
Yeah, that's illegal. I'm pretty sure you're not allowed to supplement populations. Hatcheries for whales, not a big thing. Okay, we won't do that. Okay, 30 years. Okay, what's our probability of rebuilding? We want what probability do we want to rebuild by? Was it 50%? That sounds good. Sounds pretty low. Okay, and then we hit this button that says get maximum bycatch rate. And if I've done it properly, the little thing goes white, which it has. So this is actually doing a fairly major, it's doing a whole lot of projections for different bycatch rates. Okay, and it's basically trying to find the bycatch rate that's going to get you to that goal. So there we go. It says the maximum bycatch rate to reach the goal is 0.039. So that tells us that 0.039 is the level of bycatch rate. If you can set that bycatch rate, you will achieve the goal. Okay? And we couldn't get that from the other table because it didn't have the combinations and permutations. Now you might notice it's doing some funky little dot things here. This is actually just because I'm a mathematician and I like to see the raw results. It means nothing. Don't look at it. Okay. If someone did ask me about the model, I'm not going to go through the arithmetic, but the projection model gives you the model that we're using, and also, probably more interestingly, gives the default parameters for the different life histories that we use in the tool. Okay, back to the screen. I like this two-computer thing. Okay, we did that. Let's try. Okay, so it's your turn now. What I want you to do, how much time we got? 15 minutes.
Yes.
Okay, I was hoping to have a little bit of time. So this is your mission, if you're prepared to accept it, and given you came to the workshop, you have just accepted it, is to go back to a couple of things. The first one is why there's a little picture of me sitting there. Can you move that? There we go. Okay, so what I want you to do, and I suggest you form groups because I think this works better in groups. But first is a sort of easy task. I want you to work out what PBR is if you have an estimate of 100,000, a CV of 0.3, and we know that for PBR it's the lower 20th percentile of the distribution. And I said it was a fur seal, so you're going to have to find out what the default R max for a fur seal is. And FR is 0.5. So that's mission number one. Okay. And here is a hint for those who are interested in sampling distributions. So when we estimate things, we often assume they're normally distributed, right? That's not a really great assumption about abundance estimates. Why? What is a normal what's the range of a normal distribution?
It can't be negative.
Yeah, I have to say I've been around a long time, but I've yet to see an estimate of abundance that's negative. So we use what's called a log normal distribution. So a log normal distribution is always bigger than 0, right? And it's skewed. You can get some really big values, but obviously you can never get a negative value. So this distribution needs to be log normal. Hint, Q normal. Or P norm, one of the two. So that's task number one. Task number two is is to run that bycatch tool, but essentially see what happens if you change some of the guiding principles. So instead of a CV of 0.2 for bycatch, what happens with a CV of 0.3? So more uncertain removals, but at the same time, we increase the time to rebuild. So what would we expect, right? If you increase the uncertainty, what do you think the bycatch rate would have to do? So there's more uncertainty, you would expect the bycatch rate to be higher or lower? Lower, right? Because you've got more uncertainty. But what do you think the bycatch rate to allow recovery if I increase the amount of time you've got to get there? It goes higher. So does it go up or down if I change both of them? If you know the answer, you could probably get a job to replace my job because you're smarter than me. Otherwise, you've got to use a computer, which you have to have. And then what I want you to do is to think about how you would change the bycatch, solve the bycatch case if we were using a humpback whale. And you're all online. See if you can find a better R max than my default value. And then finally, a minke whale. What sort of level of calculation would you do for a minke whale? Okay, you've got a few minutes. Okay, move.
No, I mean.
Hey, can we have the numbers back? André, can we have the numbers back?
Oh, come on.
I think we need those.
Please.
Sorry? Yeah. Yeah.
I don't know exactly what's going on.
So I just. Yeah, okay, so.
Okay.
That's what I've been meeting when I do you know where I shoot? Okay. But I think it's just that I've always seen you've been sitting down. But we're actually standing up. What a shock.
That's the leftover pool. Okay.
No, it doesn't matter. So we start here and it's 100.
No, I've got first deal. We're talking about the history of municipality foundation and it's been reduced to 1,000 for 6 years. I'm figuring we have a lot of.
I think you teach me. I lose weight.
Put it on your feet.
Because I use a lot of it.
Hey, André, is this our rank supposed to be national?
Yeah. It's 1 point something. So the point is the sorry? For Phillip, yeah.
So where do you get that information? The
Okay, I
MMBIET.
and,
Okay.
trying to it's not like
Okay, so the way you do that is you work with models. So you find out, with normal, the normal distribution, what is the percent? And then you apply that in log slips. So you work with a log of the abundance estimate, find the lower confidence interval.
So that's not in this.
No.
See, that's what I was saying. Where you have to go out of that. That's why I just want to be back.
No, it doesn't do P norm.
Yeah.
I think it's P norm.
So you gotta go back to R.
Yeah, in R, there's a function called P norm, which calculates the inverse cumulative norm. Or you can use Excel, which is in this, I think, in Excel.
Yeah, it's been a long time since I used that.
Yeah, well, that's why I couldn't remember what it was. And if it's in Excel, it's probably wrong as well. So that little detail.
Yeah.
So it says PBR, it's M, then it's the lower 20%.
How are we doing? So the
Well,
way this-
plus they're not.
it's the- it's-
They are
so you
not.
got-
They are.
so the estimate you've got distribution, right? And what we're doing is trying to find the lower 20th percentile. Not 0.2, but what is the, so you've got a distribution that's defined by the mean and by its uncertainty. And so what you want to do is you want to find, if you think about it, it's power of feedback, you calculate probability of the same calculation. If you're having trouble with PBR, we can do it manually and you can move on to the second part.
Yes, please.
All right. Here I told people to have P norm in their heads. Me, you don't know it's minus 0.84. I don't either. I've moved them on to the second part. They're fine.
Yeah.
Okay, let's knock off at least the PBR thing, and I'll see how you guys going with part 2?
You mean bullet 2
Bullet
in the
two.
fur seals?
Yep. 5 minutes.
I think there's some questions.
Some questions about
About solve for bycatch?
cyber bycatch or PBR?
PBR.
Okay, let's do PBR.
So I actually found the first part that's confusing, Andre, is the population estimate 100,000?
Yes.
Or is 100,000 the 20% out?
100,000. So the way I set that up was that 100,000 is the best. Actually, we gotta use the ball. In the
Dang
ball.
it.
Damn, I got rid of the ball. Okay, well, we're gonna use this. Oh. So that's your best estimate, right? So what is a log normal distribution going to look like? It's not going to go below 0, right? It looks something like that. So the median is 100,000. The mean is somewhere out there. So what PBR does is it uses some value X, which is such that this probability is 0.2, right? So basically the N min is less than the best estimate depending on the amount of uncertainty. So the more uncertainty you have, the lower this value is going to be, which makes sense, right? So if you've got an uncertain estimate, you need to be more conservative, okay? And the way you calculate N min is EXP of minus 0.84162. That's the magic number. That is Q norm, for those who know what I'm talking about, times 0.2, because that's our CV, times 100,000. So what I'm doing here is I'm finding the value of X such that the probability in this area is 0.2. Now, this is the CV that I'm putting in. E minus a number times 0.2. So that number is always going to be less than 1, right? Okay. And the bigger the CV, what happens to this term here? So if I double this from 0.2 to 0.4, what would the E term do? It would go up or down? Which way should it go? If you want to be conservative and you're more uncertain, which way should it go? Yay, the math works. So yeah, if you increase this to 0.4, this number would get smaller. But as written, it's 85,502. And then we multiply that by 0.5. And we multiply it by R max. For pinnipeds, the default value is
0.12.
0.12. Excellent. And then we multiply by FR. And if we multiply those numbers together, we'll get some number, and that would be the PBR. Okay. So just to recap, what were the steps? We started with our best estimate. We reduced the best estimate depending on its CV. So the bigger the CV, the bigger we discount it by. We multiply by the productivity, which is this 0.12. So for pinnipeds, this is 0.12. For cetaceans, it's 0.04, reflecting that cetaceans are obviously less productive than pinnipeds. And then we multiply by the recovery factor, in this case, 0.5. Does that make sense? You see how this system works? So it's got three things. How many animals do I have? What's the productivity? And what's my fiddle factor to take into account policy considerations? Sorry, Kristy, I just have to do it. Okay, so you've got PBR under control. Let's spend a little bit more time trying the first things. You've got it all. Just got to rerun the solve for Bycatch. How are we doing? Oh, I can see some.
Can you put
Yes, so the bit that you was put in. On that. Oh. Yes. 0. Lambda max. So lambda max is 1 plus R max. That would be seriously high, like PBR.
How did you, from the code, how did you get 0.12? I just see it entered.
That's the default value for cetaceans, 0.04, and it is 0.12. Go back to Bycatch tools and change the parameters to do with the CV of Bycatch and
This PBR 25.
yeah, 2,500. Yeah.
Did you put back the numbers for the?
Sure. Yeah. So there's lambda max and there's R max. The R max is 0.12. Lambda max is 1.12. So lambda max is 1 plus R max.
Yeah, this is a Bycatch. Yeah.
If you chose R max of 1.12, you wouldn't be managing a pinniped, you'd be managing an anchovy, which would be probably policy-wise not a good choice in terms of size of PBR. So who's doing this? You're doing this as well? How's the Yep.
We're on the advanced round.
Yeah, you set it up in advance and then you run it in solve for Bycatch. Oh, you mean the online one?
No, I did it from here. Yeah.
Oh, yeah, no, you're getting shiny drawing.
It is more.
So when I look into this, I just type.
Yep. Sure. Yeah, no, 25 Hammond. Oh, remember you got, yeah, it's the PBR was 25 out of 100,000. Well, you try and manage for that. The fishery, yeah, that would be straightforward. How are we doing? Sometimes. There's no number. To be fair, my laptop shirt is also downside and mask off.
Where are you now?
Runs my way.
For the solve for Bycatch, what's our goal?
Our goal is unchanged, but we want a 40 Oh, I changed the TV.
But maybe I have something different.
You have to go back and do all of these work.
Yeah, you have to set it up in the advance. It would have been there, but it was right when you close the app, you lost all the. Point two.
How did you know that?
That was from before, and to be honest, that's one of the most difficult things to do when you're doing any of this sort of policy stuff, because you sort of, you sort of second guess it.
Andre, you're starting to steal time away from yourself.
Oh, I got it. Myself is telling myself that we need to go to the next section. Okay, we'll have time to go back to some of this in, if we got time for question and answer session, or you may just have had enough of ShinyApps and then just not read. So we'll park that for the moment. And my boss has told me I need to get going, so I will. Okay, so the final session is going to be on what's called management strategy evaluation. So the term management strategy evaluation is used a lot in essentially in fisheries and in marine mammal conservation. And it's used to essentially come up with formulae like the PBR, right? The PBR didn't just come from Paul Wade sitting over his dining room table and going, let's find a formula, right? So what we want to do is we want to have an objective process to come up with a policy instrument like a like PBR. And Kristy used a term something testing. What did you? Performance testing. So that's a, management strategy evaluation is sort of the technical term that we use, but essentially you can think of it as performance testing. And what you should think about here is these formulae are really important, right? We don't want to get the PBR formula wrong because it has consequences for management. So we can think of there's two ways to solve this problem, right? The first way is we go to Australia because Australia will do all sorts of things just to see if it works. And we'll apply whatever formula that Simon comes up with, and we'll see what happens, right? And if it doesn't work, we'll fire Simon and try something else, right? That is not a really great policy, right? And I'll tell you the next analogy would be the pilot on the plane that's flying me back. So I'm going to fly across the Pacific. I'd like some dude who isn't just trying this out for the first time. And we hope that the pilot on my plane has been tested out before he or she is allowed to fly it. And generally they learn on real planes, but also flight simulators, right? So who's played flight simulator? Right, have you ever been able to land at Charles de Gaulle Airport? I've never been, I always crash to the ground. So
Andre, your back is to the Zoomers. Back
oh, sorry.
Right there, yeah.
So, oh my, sorry. So what I'm going to be talking about is a flight simulator for managing cetacean population. So what we're going to do is we're going to create a model, a flight simulator, and we're going to, instead of flying to Charles de Gaulle Airport, we're going to look at different formulae that could be used to manage bycatch. So if this gets complicated at any point, just think about you're sitting in front of a flight simulator, and instead of altitude, it's the abundance estimate, and instead of the balance of the plane, it's the CV of the bycatch. So keep that image of a flight simulator in mind. So some of my text has sort of gone weird on me, but we'll see how that works out. So I think we've covered most of this. Essentially, what we do in management strategy evaluation, if the text actually appeared, because it was on my slides, we have two models, just like we do in a flight simulator. We call this model the operating model. You can call it Microsoft Flight Simulator, right? It is the truth that you have to deal with. And then we have a second model, which we call the management strategy, or in our case, you, right? You're flying the flight simulator. In our case, PBR is setting, the PBR formula is setting a PBR that goes back into the real world. So this is the real world as represented on a computer. This is the management system as represented on a computer, right? Because can you see the analogy between the truth and a flight simulator and you, the pilot, and PBR type formula, right? So we're trying to manage a system on a computer rather than in the real world. And this is used very extensively, it originally comes from fisheries, where we use the same techniques to come up with what are known as harvest control rules that we use in fisheries management. So why do we do this? Well, we've got a number of reasons for doing it. Sometimes we develop these specifically for a particular fishery. So Phil referred to the International Whaling Commission, or IWC, and we've used this basic approach. Instead of using the PBR formula, we've developed specific formulae for specific fisheries. So we have a very specific way, for example, to manage the harvest of bowhead whales by native peoples in Alaska. It's not the PBR formula, it's a formula that was designed specifically for that population. The second is PBR, basically. It's can we come up with formulae that we can use for a lot of different populations? Often we can do this a lot quicker than we do here. And my personal favorite is showing that somebody's smart idea isn't going to work, right? So the good news about this is, unlike Simon applying his formula in Australia, we can show that it's not, if a strategy doesn't work on a computer, it's not going to work in the real world, right? That's a sort of a law of management. Doesn't mean it will work in the real world, but if it doesn't work on a computer, it's not going to work in the real world. And the other thing we really focus on here is uncertainty, and we've talked a bit about that already. So hopefully, you can now see the actual text. So the way this works is management strategy evaluation is the interaction between science and policy, right? So the PBR formula is one of an infinite number of possible formulas, right? Why do we choose PBR the way it's formulated rather than abundance estimate squared divided by the CV plus 14? And the reason is, firstly, because that formula was pretty stupid, but also because it doesn't relate to the objectives that we're trying to achieve, right? So what we're going to be doing is we're going to be building two models. One we call the operating model, that's the flight simulator, the truth that we're trying to deal with. And it has a variety of things in it. It's got some biology. It's got how do we generate our data? How good are our data? And then we've got the management strategy, and depending on the particular type of management strategy, we may have an estimation model. In other words, we go out and we apply some sort of analysis method. PBR is actually one of the simplest management strategies in the world because it doesn't require any really sophisticated calculation. And we go round and round and round, and then we produce performance metrics. Things like, what's the probability that the stock will be bigger than the OSP in 100 years, right? So where do I get that from? I get that from the policy statement. So we start with policy. Policy gets interpreted in mathematical terms. and we compare things using this framework. So there's some important steps here. We have to interact with the policymakers in the US. I guess it's the MMBIET itself. But in other countries, you're often dealing with ministers and stakeholders and all sorts of interesting people. So we sort of talked about this. The operating model is the reality that we're going to be testing. For the PBR, it's actually really simple. It's only biology. We don't, I think Kristy sort of expressed it quite well. When asked, well, what was the economic consideration? She said that really isn't the primary objective here, right? Primary objective is biology. But we apply this in fisheries where economics actually is really important. And so we've developed operating models that include multiple species, things like offshore wind. So if you work in fisheries, turns out offshore wind operators are more important than the fishery itself because they're politically far more important. So we try to build the entire system. For our purposes, be aware that that exists, but we're going to have a much simpler system to be able to test PDR. So just to reiterate on where I am, so MSC is as I said before, the interaction between policy and science. And so we try to divide the goals of the two. So as a scientist, you shouldn't be telling the policymakers what their policy is. And the policymakers shouldn't be telling the scientists how to do science, right? That rarely actually works that way, but that's the way it should. So what do the decision makers do? They specify what the objectives are. So this should come from the legislation or policy documents. Generally, but not necessarily for US PBR, objectives are in conflict. So how many of you have actually read the, say, the Fisheries Act in your country? It probably says something like, we should conserve the ecosystem, we should maximize the catch, we should attain full employment, and we should do that as cheaply as possible. Does it sound about right? You can't do that at the same time, right? The objectives are fundamentally in conflict. And so one of the things we have to do is to work with decision makers to help them identify the balance, right? If you want to have full employment, you're probably not going to have a stock at carrying capacity, right? You can't do that. As a scientist, I can't tell you what that balance is, right? That's not my job. I am not a politician. I am not elected. Someone being elected, that's their job. So how do we make priorities amongst our objectives? How do we quantify those? And then as scientists, we help the decision makers because they don't understand what a probability is most of the time. So when they say, we'd like a healthy ecosystem, does anyone not want a healthy ecosystem? But we all want a healthy ecosystem. But what does that actually mean? Maybe it means that all stocks are above half carrying capacity. But that's a very practical and a very modeling type of thing to do. We select a whole bunch of uncertainties, and I love this is what I do. And then we have to come up with ways to communicate with our decision makers. So I think somebody asked, what was a CV? That was a great question. Do you know how many politicians know what a CV is?
I think it's curriculum vitae.
Curriculum vitae, yeah. They want to know, when was this management strategy? When did they get their degree? How many publications did the strategy, So the communication is really important and shouldn't be done by me, right? So we bring in people who are professional communicators to create graphs that people actually understand. And these processes can really foul up if you do fantastic math and stat but can't communicate with your stakeholders. So this has been used all around the world. It started out actually in South Africa working with sardines and anchovies. I don't know how many of you follow African penguins. You know what I'm talking about? African penguins. This is a big issue in South Africa, whether the fishery is impacting the penguin population, what would happen if we closed areas. My lawyers have told me it is not in my interest to comment on that particular issue, but it's a very interesting issue and one that we've tried to build an operating model, remember that flight simulator, that includes the fishery and the penguins, so that we can sort of go to the decision makers and say, if you want lots of penguins, you're going to have a small fishery, right? You can't have the big fishery and all the penguins. In Australia, we've used management strategy a lot. in particular, and Simon will know this fishery because I think this southern shark is now included in this. This fishery down here is what we call the southeast fishery. It is our most complicated fishery in Australia and has every known problem that you can imagine, including you deal with school shark and sea lions, right?
Yep, and gummy shark.
Yep, school shark, gummy shark out here is Simon's territory. So we built a management strategy for that particular fishery that includes economics, multiple species, bycatch, everything we can think of, and we still filed up badly, but we won't talk about that. But it's been used extensively in a really ecosystem context. In Alaska, we're using the same approach. We've already heard about climate change. So what strategy should we use given we don't really know what's going to happen with climate change? Marine mammals, it's been a focus for marine mammals. Most of my research has been on MSC for marine mammals through the Whaling Commission, in particular. How do we sustainably allow for aboriginal harvests of gray whales and bowheads and minke whales in Alaska, in Russia, and in Greenland? And Paul Wade, whose name you've heard a few times, has been involved in this. The objectives for Aboriginal whaling are very different from the objectives that we might hear about from PBR. So first one sounds familiar: rebuild depleted stocks. Sounds good, but that's an objective that specifically we have to take into account when we're building our control rule, which is that Aboriginal communities should be able to harvest whales in perpetuity. And that's a really important point. So if you're talking to a commercial fisherman, what do they want to do? They want to make as much money generally now, right? Whereas from a cultural point of view, you're looking at perpetuity. So it's a different set of objectives, and it's important in how we design our management strategy. Many of you will know that Norway still hunts minke whales commercially, and this approach has been used essentially to supply the Norwegian government with a control rule that will achieve a reasonable balance between risk and long-term catch. We'll talk about that. Okay, what happened to my PBR formula? It's even been more cut off. So MSC, or performance testing, was used by Paul Wade to come up with the PBR formula. So how did it compare bits? So we've used, I'll go back just to say that's the PBR. PBR formula. We've actually used management strategy evaluation to compare different versions of PBR. So, for example, most applications of PBR just use the most recent abundance estimate, but maybe you should use multiple abundance estimates going back in time. And a paper that was written by one of my ex-grad students essentially came up with a new version of PBR that used multiple abundance estimates instead of the most recent one. And we showed that that led to less variability in PBR itself. So one of the things that really kills fishers and fishing communities is catch limits that vary a lot from one year to the next. If you know what the catch limit's going to be and it's going to be fairly constant, you can plan. But if it's 0 in 1 year and 1,000 in the next year, that makes it really, really hard. So we looked at that issue. So now, I always get terrified because Kristy is here and knows the system a lot better than I do. But how did PBR come to be? Well, the goal as specified in the US Marine Mammal Protection Act, what I call the conceptual goal, so there's no map here, right? So the goal is to allow each stock to reach or maintain its optimum sustainable population. That is what the specific legislation says. However, this is not a term that has any meaning in biology, right? It's an MMBIET thing. So if you go to a biologist and say, well, what is optimum sustainable population? They'll say, duh. You know, it has no meaning. So it was defined. And in this case, it's defined as the number of animals which result in maximum productivity. Note that I'm making this more specific now. This is this interaction between decision makers and scientists. And there's a whole bunch of text that you can't read, but it's all about caveats. No. We'll get there. We can go back to it. So that was that stage. Oh, just move my. So those were the goals. Those are the goals, but they're not very mathematical, right? To define a goal mathematically, you need to turn it into things that we can actually compute as scientists. So the way this, I'll get to it in a moment, there are multiple ways to do this, but one of them was the probability above MMPL, which means OSP, after 100 years of management based on PBR. So I've gone from it should rebuild and stay above OSP to what have I done? I've defined what I mean by OSP, and notice I've added a timing, right? So I'm being more specific. I'm not very specific yet, and I'll get to that in a moment. But note how I'm interacting between policy and what we call science. Yes, Paul Powell.
Do you know why 100 years? I mean, what is that magic century about?
I believe we need Paul Wade here. My guess is it relates to the fact that at the same time this work was being done, myself and others were working in the Whaling Commission, and we used 100 years. My guess is that the US saw what was going on and decided to use the same number. And where does the original IWC number come from? Well, no one knows.
That explains it.
But it turns out that you can translate 100 years into 50 years. There's a translation to it. But there is a certain amount of arbitrariness in all of these things, because you always have to make a decision. So this work was taken further, and there are a number of other goals. There's a carrying capacity goal, which basically says we just don't want to hit OSP. We want to get as close to carrying capacity as possible. So very different from an exploitation goal, where you'd want to be around maximum production. There's a recovery rate goal. There's a 20-year goal. And each of these was quantified by a specific performance metric. And I think, Kristy, you raised one, was the probability of being above OSP was 95% after 100 years, for example. So can you see how we've taken this very high-level policy goal of do good things to the marine mammals to we want a 95% probability that a stock will be above OSP in 100 years. Okay. So let's delve down. Now you remember my flow chart that had policy on one side and science on another. Now let's go and have a look at the science side for a moment. So here is my operating model. So remember, that's the flight simulator. Okay, that's the truth that we're trying to model. So the model of the truth that Paul Wade used was what's called a theta logistic equation. So that's just a very simple population dynamics model. It doesn't capture age, it doesn't capture sex, etc. We also modeled the process of, he did. When Paul did his calculations, he allowed for the fact that if you set a PBR, the actual catch that you get isn't going to equal PBR. It's going to be around PBR, you hope, because you've got to implement regulations and those don't quite work out. So in his case, what they did was they said the actual catch equals PBR times a random component. And Paul, interestingly enough, also put a bias in here that, for example, you may set PBR, but you've got an illegal bunch of fishermen who don't follow PBR. So if you set a PBR of 100, you're maybe going to get 110 instead of 90, right? So it's not just noise, it could be systematic bias. And remember, I talked about uncertainties, right? So one of the key things here is to identify, what are we concerned about? We also had abundance estimates. Again, there was a bias. Maybe we screw up how we do our calculations. So we generate two things, the catch and the abundance. And then what Paul Wade did was he did some simulations, rather like the tool I just showed you. And he did two calculations. Now, when people look at the PBR, they say, where did 20% come from? Who didn't think about that when I told you that it was the lower 20th percentile? Why wasn't the lower 15th percentile or the median or right? This is where it comes from. So what he did was we started with a population model with default parameters, and remember lambda max. That's where that comes in. Very simple. We had no biases, no catch, no abundance bias. We have two levels of the CV of the abundance estimate. So 0.2 CV, as Phil Hammond pointed out, is really good, right? Remember he was saying this morning that his 0.3 was good. 0.2 is obviously even better. And then we had the really bad survey. CV of 0.8 basically means that if a population is really 10,000, you could estimate it anything from about 100 to 10 times bigger than the true value. So CV of 0.8 is huge, but is not at all uncommon for things like beak whales, for example. A CV of 0.8, when you're using hydroacoustics in a population, you don't even know what the species is, you can get a really bad estimate. And remember, this is all about covering the uncertainty. For a cat CV, for the moment, we've set FR equal to 1, so the recovery factor is set to 1 with our two levels of productivity. And then we did a whole lot of forecasts for different percentiles. So we tried to look at 5%, 10%, 15%, 20%. And what did we do? We found the percentile that led, Kristy, to a 95% probability of rebuilding to OSP in 100 years. So can you now see how I've linked the policy goal, which says recover marine mammals, to a performance metric, which is rebuild in 100 years with 95% probability, to a specific element of the control rule, which is the lower 20th percentile. So those are totally linked, right? So if you change the policy goal, you'd change the 20%. Yes?
Why is the catch CV so precise?
0.3. I don't know. But it is. What we'll show in a moment is that we didn't just use that one CV.
Oh, okay.
So Paul, and this was his PhD, I'll show you in a moment which ones he looked at. Subsequent to that, Carla and I and other colleagues have looked at a whole range of which are the most important things. It turns out that variability isn't nearly as important as bias.
It's just not that sensitive.
Sorry?
So it's just not that sensitive to it.
No, variability is bad. You don't want it, but bias is the thing that really kills you. So if you consistently overcatching PBR, that's far worse than if you're randomly around it, right? Same with abundance estimates. The worst thing you can do is overestimate abundance consistently, right? And I don't know if I got a figure to show that.
The error that he incorporated on the earlier page, the random error, was that forced to be conservative or was it bi-directional?
This one is, well, okay, good question. The random error is random. So it can be, you could basically, if you set a PBR of 100, you can get with equal probability 50 or 150. The catch bias is the thing that kills you, right? Because that's the one that says you'll be consistently above or below PBR. To be honest, we didn't really care about below PBR because it's the above PBR that matters. So
that was skewed.
That's definitely skewed, yeah. Okay, where am I? Oddly enough, it's taking longer than before. I think we've got an empirical evidence that everything takes longer. So let's go to this. Okay, so let's recap. We've got our 20th percentile, right? We don't have FR because when I did this calculation, I assumed FR equals 1. FR is the measure that takes into account uncertainty. So what Paul did was fixed N-min to be the lower 20th percentile, and then started changing things. So what happens if there's bias, right? And it included quite a large amount of bias by 50%. So what happens if you set a PBR of 100 and on average you get 150, right? And as you can imagine, that will swamp that CV of 0.3. The 0.3 sort of goes away once you do that. What happens if R max is not what you think it is, right? So we're assuming 0.04 for cetaceans. I haven't done a lot of work on dolphins, but everything that I've seen with dolphins compared to baleen whales, is baleen whales are the rats of the sea. Someone actually said that. They do seem to reproduce early. They seem to increase quite nicely. I mean, all the baleen whales I've worked on are rebuilding. I mean, bowheads, gray whales, humpbacks, right whales, except northern right whales, but they're special. the baleen whales are doing great. The dolphins are just not, they're just not rebuilding like we think they are. I mean, Hector's dolphins in New Zealand are a classic example. They've done everything they think they can and nothing is helping. So maybe for some of our populations, 0.04, it may be correct on average, but it sucks for some species. So we did simulations with a lower value of R max. What could happen if you got R max wrong? What about a nasty one that the CV is 0.8 for the survey, but André does the analysis and gets the formula wrong and gets the wrong CV, right? So remember, the CV of the abundance estimate is the amount by which you reduce the best estimate to get N min, right? If you get that CV too small, you're not going to be conservative. So we looked at that. How often do we update PBR? I think we didn't quite get, we're supposed to be every 4 years. How close is the US to doing updating PBR?
Oh, it totally depends on the abundance surveys.
It can be anything up
We
to
don't
8
usually
years.
update the stock assessment unless we have new.
So the default was 4, we doubled it to 8, we changed the MMPL. And essentially, yeah, again, I'm not going to go through this, but there were things that really mattered. And the things that mattered the most, it turned out, were these biases, in particular the abundance bias. So if you want a good management system, count the animals correctly, right? Did we just spend a whole day for me to conclude that you should do a good survey? But you should do a good survey. And so that FR value was selected, the default of 0.5 was selected to be robust. And that's a really important word in management strategy evaluation. To be robust to a fair level of all of these biases. If all of them happen simultaneously, we toast, right? That's like you're flipping a coin 6 times and getting heads. Just, yeah, that's tough. But essentially a 0.5 is robust against a little bit of catch bias, a little bit of abundance bias, getting the R max wrong, et cetera, et cetera. So that's where that came from. Since that work, this is a paper that I led as part of this project. We took the PBR and we asked more sort of sophisticated questions, things that couldn't be done in 1998. So the first thing we did was we said, that beta logistic model is really cool, but it turns out that cetacean populations have age structure and sex structure. And in many cases, the bycatch is not random across age classes and sex classes. It may be female biased, etc. So we built age structure models and sex structure models. So what we're doing here, what are we doing in our flight simulator? We're taking out one part of the flight simulator, and instead of landing at SeaTac Airport, we're now landing at Charles de Gaulle, and we all know that's really hard. But sorry, it turns out you have to land at Charles de Gaulle sometimes. And it turns out this was consequential because age and sex structure lead to time lags in population dynamics. So if you've got a depleted population and you stop harvest, it only affects the youngest age classes, right? Because they're the ones that are going to be the new recruits. You can't change how many 10-year-olds you've got because they're there, right? So there's some time lags. We built in catastrophic events. Since the work that was originally done, we've now got a pretty good idea, particularly for pinnipeds, of these catastrophic events where you lose maybe 20 or 30% of the population because of a disease or something, right? So let's build that in. We looked at multiple stocks. This was particularly relevant for the import provisions issue because what happens when you've got a country, okay, I always wanted to be a country, but never seemed to happen that way. Let's pretend that I'm a country and I have 2 fisheries. For, let's say it's a marine mammal stock, it's depleted. I have 2 fisheries. One of them exports to the United States. The other one is domestic. Will my domestic fishery be on the list of foreign fisheries? She says no, right? So what that means is, as a country, I've got to worry about Kristy taking my export provision away. So I'm going to, personally, she wakes up in the morning and goes, André. So I'm going to pay attention to my export fishery. I may not pay that much attention to my domestic fishery because the incentive is different, right? There's conservation incentive, but there isn't the incentive that I can't export to the United States, which as a country I care about. So we looked at, what are the consequences of that? And then we played around with harvest with bycatch that was focused on different age and sex classes. It generally came out that PBR worked really, really well. PBR is an amazingly robust technique. if you have all these things together, it doesn't quite achieve the performance goal that you would start with, but it does do what the MMPA wants, which is it rebuilds stocks at least in the right direction. So, do we have any time? Do we have any time, boss?
Yeah.
How much time do I have? Brilliant. Okay. Okay, everybody, who has a file called PBR parts? An R file called PBR.
PBR 4 parts.
Okay, load her up. Okay.
I feel like at some point, I would like to better understand how the F values are chosen. Because I feel like that's just like a little bit like the Wizard of Oz.
We come from Oz.
I mean, like, it's just like you don't really know what's going on behind the screen, sort of.
Are we talking about the recovery factor?
Like,
The FR value?
yeah.
Talk, Kristy, I'll hand over the.
I mean, I'm really not the best person to ask for this, but I believe that those default values were chosen based on a number of factors, like using 0.1 for endangered populations or those that are on the red list. That, I mean, it's all gonna.
It's more, I mean, it's almost, I mean, they ordered correctly,
Yeah.
right? But exactly how, I mean.
Yeah, like, is it really 0.2 or do you want us to 0.3 because, you know, we don't know enough about this other, like, I mean, all these others have like equations behind them, and that one I feel like is more of an expert decision system.
Well, the 0.1 was based on some analysis, so it was what happens to a population at really low size. And one of the issues that Paul didn't deal with originally is things like, if you've got a really small population that's highly depleted, what's called demographic uncertainty starts to come into play. So you've got an anchovy, no one cares whether anchovy number 5,000 dies or lives, right? It matters a lot when you're down to 50 animals, right? So part of that 0.1 is a qualitative accounting for the fact that there's a whole bunch of unmodeled stuff that happens to small populations.
Yeah.
And the first thing you do is you get them away from being small, and the 0.1 helps.
That makes sense, but like the gradations between, it's hard for me to know, like.
I think that was almost certainly a committee that came up with those. I mean, again, it's qualitatively correct that the ordering makes sense, but you know, it's even with all those formulas, this still operates in a policy forum, right? So there's, as Kristy said, I mean, like the TRT, there's a whole bunch, there's no formula that says you have 14 pingers and 2 closed areas. And so anything to do with policy involves trade-offs with stakeholders. And so you can never, as much as a mathematician would like it, you never end up with a formula-only approach. Right? But the formula guides the system in a major way. So, you know, does Australia use PBR at all for anything? I mean, they calculate it. I don't think they use it. Yeah. So the US is pretty unique in terms of having a control rule that, while it doesn't force anything, you know, if you're above PBR, that triggers things, right?
Exactly.
So you know, we're a long way away from being completely formulaic, and in fact, our governance structure doesn't allow it. You always have to have public input, right?
Let's do our hands-on.
Oh, sorry. I really enjoy this stuff. So. Strangely enough.
We will have some extra time for discussion at the end, and if we want to return to
Yes,
this,
boss.
then we
I
can.
have some resources here.
Yeah. So we can come back to that at 5 o'clock. Okay. So has everyone got the code running? Okay. What are we gonna? Okay. So what? Okay, so I'm not going to go through the code. There's a lot of it. But what I am going to do is I'm going to, this is go to the bottom of the code. So this is probably the most depressing piece of code we'll ever see. Do you know why? Comments are overrated. This piece of code, which I wrote in maybe 3 hours, is half of a PhD in 1998. Is that depressing or what? I mean, in 1998, this took this was half a PhD. Now I'm going to talk about it in 5 minutes. It's like, oh, I feel so bad. Anyway, so what I've done here is set up. Keep shaking your head at me again. So what we've got here is some specifications. You're going to be able to play around with the simulator. So you're going to be the guy who's designing the flight simulator. So survey frequency, how often do we do surveys? How often do we update PBR? What's the abundance bias? What's the catch bias? You don't like the CV of 0.3? You can change it. What's the CV of the survey? What's the true value of RMAP? So those are think of those as the parameters of the flight simulator that define the scenario. Here is the control rule that we're going to test. So the true RMAX is 0.04. I'm going to assume 0.04, so I'm going to get that right. This thing here is this is the correction factor to get the lower 20th percentile. But you can change that. You can look at lower 30th or lower whatever. FR is currently 1. I'm assuming that I get the right value of the survey CV. So run this piece of code and see what you get.
Right, we have to run the stuff about.
Just hit this. Okay, for those who haven't done it, hit the source button. So if you hit source, it'll run the entire program. Does everyone get a graph? Okay, let's run it and get the graph. Let's have a look at it. Okay. Okay. Oh, there's the little. Okay. So,
between survey frequency and update frequency?
So survey frequency is how often you do a survey. Update is how often you recalculate PBR. So you might do a survey every 4 years, but you only update it every 8 years, for example, because of your process. So what this shows, in this particular case, we've got a stock. So RPAR is RMAX. Init depth is the population size relative to carrying capacity. So this is saying that we're starting at 30% of carrying capacity. And I'll tell you what Tessa is in a moment. So what this shows is what's the probability of reaching MMPL and getting above MMPL. So if you start at 30% of MMPL and MMPL is 0.5, what's the probability of being above MMPL? You're at 30% and you need to be at 50, you're below, right? So it starts out at 0 and then slowly and stochastically it increases. And it doesn't quite get there in these simulations, but I think that's nothing to worry about. The red line is 95%. So that's the target. And in fact, based on 21st century calculations, it's about 93% probability of rebuilding. So we don't quite achieve 95, but you're going to fix that up. Sorry, 91.4. This is the population size in 100 years relative to MMPL. So you can see most of the population is above, but that's not 5%. And these are the catches. But we're not going to worry about those for now. So the first thing is you are working for who works for a conservation group? Okay, your conservation group is to sue the US government, and because they claimed it was 95%, right? She said so, she works for the government. What do we conclude? Look what it says. Probability of rebuilding is 91.4%. Right? Your first mission as an now employee of the United States government is to find a new value for this 0.8 so that it gets to 95%. So what you need to do is you need to go into the code, change that, and solve for the new control rule. We can call that PBR SSM 20, whatever year we're in, 2022. So this is the 2022 PBR. So go into the code, play around with different values of that 0.8, and see if you can get it to rebuild with 95% probability instead of 91.4. Yes.
Can you repeat what init depth is?
The initial population size relative to carrying capacity.
Initial population size relative to carrying.
Yep.
What are we trying to get to 95?
Yeah, she said it was 95, remember? But, you know, it's 91.4, and that's too low. You guys need to fix it.
So André, I didn't get any, when I ran just as it was.
You need to increase, you need to close this thing down. So your graphs close. Click that.
There we go, that's good enough for now.
Oh, sorry. Sorry. If you rerun that, now there you go.
No. Sorry.
Oh, you're not, if you go use back arrow key. Oh, oh. Did you hit source?
To put in our folder.
Oh. Oh. You stored it, presumably you downloaded it. If you put it into a different folder, so what's happening is when you run source, it just saves, so if you've changed it or right. But because you've saved it in a download folder, that's an administrative folder. No, I think you're in a download folder.
Oh, okay.
Yeah, so just move it to like C colon, workshops. How are we doing? Did the point 8 go up or down? Is that the right direction?
Oh, there, we nailed it. With a 0.1.
Point 1, you're going to be so, the fishermen in the US are going to be so happy with you.
I'm sure it'll turn out that way as well. I'm highly confident in that.
How are we doing? What you just did would have taken about a week in 1998.
I feel like someone should have just.
You can't, it's not on this. No, you have to do it. How are we doing? Does anyone, first, okay, so everyone get the same numbers? So I got a 90, you had a 95? Any other answers? 94.9? Wow, that's not going to go down well. Okay, so the one thing about the simulation, which is the sort of thing we saw with Jeff, is
Back up.
I travel, don't I? I should have one of those
A
kitty.
tether?
A tether, yeah. The one thing that we need to do is to recognize that this was done with one set of random numbers. There's, I think, 1,000 simulations I'm doing, but there's stochasticity involved. So why don't you add another line, copy this line down and rerun with your selected P norm. So just add another line and run it twice. And you should get 2 sets of graphs and 2 numbers.
Oh, that's maybe why the first
Tell me what you get now. You should get the same number that you got the first time, but you get the same.
Oh, that's good.
Oh, it is. What did you get?
95 the first, 95.3 the second.
Oh, now the fishing industry is going to sue you for being overly conservative. Do that a couple of times and just see how stochasticity comes into these calculations.
But my 95 was so pretty. So we're still on the side of good.
Yeah, that's an interesting policy statement. So what we would usually do is do like 100,000 simulations to be really sure that the random numbers aren't coming into play. Okay, so let's go back to point 8 because it turned out you got sued again and the whole thing got thrown out because of stochastic variation. So let's go back to point 8. Let's see what happens when there's a catch bias. So remember, we learned from Phil about the importance of doing our calculations correctly. Let's say there's a 30% bias in our survey abundance estimate. So go in and change, I think it's called abund bias, and make it 1.3 and then rerun the calculation. Tell me what happens to those little graphs.
1.3.
1.3 for the catch bias. So what happened to the percentile? It was 90.
0% recovery.
Yeah.
Oh, okay.
Everyone's out of a job.
Oh, no. Lawyers are, we're employing more lawyers on, everyone's employing more lawyers. Okay, so am I actually applying the PBR that you saw though? No. What? This is a PBR with a FR of 1, right? But in reality, we would probably use, because this is a depleted stock, so we wouldn't use 1, would we? Our world expert on PBR says, no, you idiots, what are you doing? 0.5, that's what we should do. So go in and change FR to 0.5 and see what happens.
With
Well done,
still the
Kristy.
bias in abundance.
Yeah, keep the bias there, but let's try a 0.5 on the,
Which line is the F?
101.
here it is. right.
101.
Yep. Things looking better?
No.
Yes.
So I saved it
It's
somewhere
just
else.
as wrong
and
as
it says the source, but it doesn't tell
Yeah,
you.
now it's 100%. Yeah, but the Fisher.
Oh, sorry, source.
Frustrated.
Seriously, running some-
I mean, like, right, most of
Sorry?
the things are angler.
Well, it doesn't give it a,
That would be.
correct. This computer probably needs to.
It does.
Okay, how are we doing? How are we doing?
Everybody's saved.
Things looking better?
Yeah.
Okay, should we make life better or worse? Okay, let's make things worse. Who believes in catastrophic events?
If you don't, just wait.
Okay, so apparently there's something called climate change. Is that going to be good or bad? It's not going to be good. Okay, depends who you are. Okay, the thing called kata is the probability of a catastrophic event. Okay? In any given year. And if you have a catastrophic event, I think you lose 20% of your population. Okay? So how about, I mean, I'm a conservative sort of guy. Let's just say there's a 1% chance, don't laugh, Kristy. Let's just call, let's say in any 1 year in the future, in the next 100 years, there is a 1% chance of a catastrophic event. So how many catastrophic events are we going to expect? 1. Is it guaranteed to be 1? Not if it's stochastic. And what are we dealing with? We're dealing with stochastic calculation. So what matters here is not the mean. What matters is the tail of the distribution, right? You get 3 catastrophic events in a century, you're going to lose 20%, 20%, 20%. Are you going to make 90? You're going to make MMBIET? Got it. Put in 0.01 and see what happens.
Which line is the canopy?
104.
Yeah, right here.
That's the last line.
Yeah, so change that to 0.01.
Are we leaving the rest as if like FR.5?
Yeah, leave it at 0.5.
Gosh, we're really being rough.
What happened?
Oh, we're still doing okay.
Pretty close to 95%.
Okay.
If you round, you're not getting sued.
We're doing good.
Okay. 5%.
No.
Yeah, maybe that's what it is.
So change it to 0.05. What happens?
I feel like there should be graphics with this where there's like animals like cheering or falling over.
So you know what I used to do, but I didn't for this, is go, if you're online, go dying Pac-Man sound.
Yeah.
So everyone, just do a quick Google search for dying Pac-Man sound and run your simulations and then click the button. There's some truth to that. Come on, someone must be able to get that going quickly.
The old Pizza Hut, like arcades.
Some of us spent a lot of time in the arcades in the 80s. Some of you were born in the 80s.
Donkey Kong.
Yeah, I played I was very good at Donkey Kong. Okay, so that's what happened to the stock, right? So 5% doesn't work. Okay, but let's recircle here, right? Okay, stop that now. Let's reorganize ourselves. So that 5% didn't look good, did it?
No.
Right? So what's the most conservative thing we can do?
And that's what happens when autoplay and autograph.
Really? Okay. It's near the end of the day. We can enjoy ourselves. So what's the most conservative thing we can do?
What do you mean conservative?
We've got these catastrophic events. We're not rebuilding, right? From a bycatch point of view, what's the most extreme we can do? We're going to close every fishery in the entire country. And the way you can do that is change the 0.8 to 0.9999999. Tell me what happens. Q norm 0.9999999. Don't put in one.
That's the, whether you're taking.
So we're now making n-min 0, basically. Or you could FR equals 0 would do the same. Okay. So what happened? Is things, are we good?
No.
So does that mean that someone should sue the environment? Because the environment, it's not the fishery that's causing the problem. The catches, I presume, the catches all.
We could argue about that, Andre, right?
Yes, we
If
can.
the stock wasn't depleted by bycatch in the first place, it might have been more resilient to
Ah.
catch.
Thank you for your input. I will take that on board. Okay, so what you've just told me is even if bycatch equals 0, this stock isn't going to rebuild. What we've entered into is a scenario, a situation where there is a scenario, there is no policy solution, right? So you then have to go into a new world of policy discussion, which is what is the goal? And the US hasn't had this yet. What is the goal when you can't rebuild, even if you close any fishery? What is the policy goal? I don't think in fisheries, we haven't had that discussion. Yes.
Well, we have in the MMBIET, right? We just haven't done the same work we have done with turning into translated science as we did with the first one for the OSP, because the second one is that the species must retain its role, the same role, and maintain the role
Right.
of the ecosystem. So I think we just need to do what we did.
We
explained with the OSP, do with the lower.
right. I think that's right. I mean, what we need to have, and we're not having it in the US or probably anywhere in the world, is with climate change, what is the policy goal? What is the correct answer under climate change? We don't know. I mean, the simulations you've just done, which are not too far from what we do in fisheries, suggest that if there's major increases in catastrophic events, we will not be able to achieve the MMBIET goals. These animals will not be, whatever their role in the ecosystem is, may well change. So what this does, this MSE system, is opens up the questions about the broader policy goals, right? We got some great policy. I have to say, what the US did with the MMPA is state of the art, better than most places in the world. But it hasn't really thought about, what are the implications of climate change, right? Maybe we change our goal from 95% probability of rebuilding to just keep the damn thing from not going extinct, right? But we need to think about that. How's my timing doing? I'm over. Apparently I can talk for a long. No. Okay, I'm going to stop there. Hopefully all of you, the aim of this session was to introduce you to management strategy evaluation. So the flight simulator of the policy world. Where did PBR come from? Is PBR robust? And what is it robust to? And what is the interaction between policy and science, and where the two interact? And with that, I will pass it to Tessa, who knows